across the ancient world, there are places that seem to have outlived the civilizations that created them. Empires rose and fell. Languages evolved and disappeared. Borders shifted countless times. Yet certain monuments, cities, and structures remained, watching history pass around them. What makes these places fascinating is that survival alone was never guaranteed. Many endured wars, earthquakes, floods, and centuries of neglect. But even when the stones survived, the knowledge behind them often did not. Today, researchers can calculate dimensions, analyze materials, and reconstruct timelines with remarkable precision. Yet, some of the most important questions remain exactly where they have always been. Why was it built? What knowledge made it possible? And what parts of the story vanished long before anyone thought to record them? Northern Belize hides one of the strangest survivals in the ancient Maya world. Beside the dark waters of the New River Lagoon, Lamanai rises from the rainforest like a city that refused to die. While most Maya capitals collapsed more than 1,000 years ago, Lamanai continued to survive for over 3 millennia. And hidden beneath its towering temples and giant stone faces lies one of the most overlooked engineering mysteries in the ancient world. Unlike many Maya cities rediscovered through dramatic expeditions, Lamanai was never completely forgotten. Local communities had known about the ruins for centuries, but systematic archaeological investigation only began seriously in the 1970s under British archaeologist David Pendergast of the Royal Ontario Museum. As excavations expanded, researchers realized they were not uncovering an abandoned ceremonial center like Tikal or Kapan. They were uncovering a city that had remained continuously occupied from around 1500 BCE until the 17th century CE, an urban lifespan of nearly 3,000 years. That timeline alone stunned archaeologists. Most major Maya lowland cities experienced severe collapse during the Terminal Classic period around the 9th century, likely caused by drought, warfare, ecological exhaustion, or political instability. Tikal's population may have fallen by more than 70% within decades. Kupan experienced rapid depopulation after years of deforestation and soil depletion, yet Lamanai continued functioning long after surrounding regions declined. Even Spanish missionaries arriving in the 16th century found an active settlement still operating beside the lagoon. The first mystery was geographical. Lamanai should not have survived. The city sits in a humid tropical environment with annual rainfall often exceeding 2,000 millimeters. The surrounding terrain is unstable, swampy, and vulnerable to seasonal flooding. In modern engineering, constructing large stone architecture on waterlogged sediment requires deep stabilization systems and careful load distribution. Yet the Maya builders of Lamanai erected massive temples that still stand after more than 1,000 years of erosion, storms, root penetration, and seismic movement. Geological analysis revealed something unexpected beneath the structures. The builders had created layered foundation systems using compacted limestone gravel, dense clay, and organic fill materials arranged in alternating strata. This design appears to have dispersed weight while absorbing movement from soft ground beneath the city. In effect, the foundations behaved similarly to modern floating substructures used in unstable wetland environments. No written Maya records describe this technique, yet the physical evidence suggests the builders understood soil behavior with surprising sophistication. One structure in particular dominates the skyline, the High Temple. Rising approximately 33 meters above the jungle canopy, it remains one of the tallest surviving Maya structures in Belize. Archaeologists estimate that its construction required tens of thousands of tons of limestone blocks. But the region lacks large draft animals, iron tools, or wheeled transport systems capable of moving such weight efficiently. This creates a logistical problem that researchers still debate today. Experimental archaeology has shown that moving multi-ton limestone blocks manually through tropical terrain is extraordinarily difficult. The dense rainforest surrounding Lamanai would have dramatically slowed transport. Some researchers believe the Maya transformed the lagoon and river network into a hydraulic transportation corridor, effectively turning waterways into ancient cargo routes. Canoes capable of carrying several tons may have transported stone closer to the construction zones before human labor completed the process. Yet even with water transport, the organizational scale required remains staggering. The labor force itself raises more questions. To sustain projects of this magnitude for centuries, Lamanai needed stable food production, political coordination, and long-term resource management. Evidence suggests the city developed extensive wetland agriculture around the lagoon, possibly including raised fields and controlled water systems. Satellite surveys and sediment analysis indicate that portions of the surrounding swamp may have been engineered to improve farming efficiency during seasonal climate fluctuations. This may explain why Lamanai outlived other Maya cities devastated by drought. Paleoclimate studies conducted across the Maya lowlands reveal a series of major drought events between approximately 800 and 1100 CE. Some lasted decades. Reservoir-dependent cities suffered catastrophic decline as water systems failed. But Lamanai's location beside a permanent freshwater corridor may have provided resilience unavailable elsewhere. The city was not isolated from climate stress. It simply appears to have adapted better than most. Yet the most disturbing mystery at Lamanai is not its survival. It is the faces. Along one of the city's ceremonial structures stands the famous Mask Temple, where enormous stucco masks emerge directly from the architecture. These giant faces, believed to represent Maya rulers or deities associated with cosmic power, are among the most visually striking sculptures in the Maya world. Some stand several meters tall, with intricate facial contours, layered headdresses, and preserved structural detail that should not still exist. Because under normal tropical conditions, stucco should decay rapidly. Traditional Maya stucco was made primarily from lime plaster created by heating limestone at extremely high temperatures, then mixing the material with water and binding agents. In humid rainforest environments, this surface usually cracks, absorbs moisture, and erodes over centuries. At sites like Tikal, many exposed stucco decorations deteriorated heavily after long environmental exposure. Yet portions of the Lamanai masks retained remarkable stability even after more than 1,000 years. Chemical analysis of surviving plaster fragments revealed unusual composition patterns. Researchers identified differences in mineral ratios and traces of organic additives not commonly seen in standard Maya plaster recipes elsewhere in the lowlands. Some specialists suspect the builders may have experimented with locally sourced botanical compounds or modified lime processing methods to improve moisture resistance. If true, this would represent a level of material engineering rarely associated with ancient Mesoamerican construction. Even more mysterious is the structural adhesion of the masks themselves. Massive stucco surfaces attached to stone substructures in tropical heat and rainfall should gradually separate as expansion, contraction, and biological intrusion weaken the bonds. Yet several sections remained attached with astonishing durability. Some archaeologists compare the survival rate of these masks to Roman hydraulic concrete, which also achieved unexpected long-term resistance through highly specialized mineral chemistry. No definitive explanation exists. The orientation of the city introduces another layer of mystery. Unlike cities such as Chichen Itza, where astronomical alignment dominates architectural planning, Several structures at Lamanai appear oriented toward the lagoon itself. Reflections of sunlight across the water may have played ritual roles during specific seasonal periods. Wind direction, water flow, and visibility corridors seem integrated into urban placement patterns. This suggests that Lamanai's planners may have developed a combined environmental ceremonial system, one where hydrology and cosmology were fused into the architecture itself. Then came the metal discoveries. Excavations uncovered copper bells, metallic ornaments, and evidence of long-distance trade connections extending south toward Panama and Costa Rica. Metallurgy was relatively rare in the Maya world compared to civilizations farther south, yet Lamanai appears to have participated in technological exchange networks that connected distant regions of Central America. Some copper artifacts discovered at the site date to periods when many Maya centers were already declining. This implies that Lamanai remained economically connected, while neighboring systems fragmented. Trade may have been another reason for its longevity. What do you think made Lamanai survive for nearly 3,000 years while so many other Maya cities collapsed? Was it advanced engineering, environmental adaptation, or something we still don't fully understand? Share your thoughts in the comments below. Cumbemayo sits more than 3,300 meters above sea level in the northern Peruvian Andes, roughly 20 kilometers southwest of the city of Cajamarca. The site was first documented in detail by modern researchers during the 19th and early 20th centuries, though local communities had known about the strange stone canals for centuries. What immediately shocked archaeologists was not the scale of the ruins, but the engineering hidden inside them. Carved directly into volcanic rock was an artificial water channel stretching nearly 9 kilometers across mountain terrain, where such precision should have been almost impossible for a prehistoric society. Radiocarbon studies and ceramic analysis suggest that parts of the complex date to roughly 1500 to 1200 BCE, making the system more than 3,000 years old. That means Cumbemayo existed long before the rise of the Inca Empire, and possibly even before many of the sophisticated hydraulic systems of the ancient Mediterranean world. Some researchers now classify it as one of the earliest known large-scale water management systems in the Americas. The first surveys revealed something even stranger. The canal was not built randomly downhill. Instead, it maintained an extremely controlled gradient over long distances, guiding water through harsh Andean rock formations with a level of planning that many historians did not expect from such an early civilization. The central mystery of Cumbemayo is the canal itself. The structure cuts directly through volcanic bedrock, sometimes only a few centimeters from steep drops and fractured stone surfaces. Even after thousands of years of earthquakes, seasonal flooding, and extreme weather, parts of the canal still function. Modern hydraulic engineers studying ancient water systems have pointed out that the canal's slope appears intentionally optimized. If the water moved too slowly, sediment would accumulate and block the flow. If it moved too quickly, erosion would destroy the channel walls. Yet Cumbemayo balances these forces with surprising precision. Some sections contain sharp zigzag turns that seem unnecessary at first glance, but engineers now believe these bends may have acted as primitive hydraulic brakes, slowing the water and reducing pressure damage during heavy seasonal flow. Similar concepts appear in much later hydraulic systems, including Roman aqueduct overflow controls and Nabatean water channels at Petra, yet Petra flourished more than 1,000 years later. Researchers comparing the gradients of Cumbemayo to modern irrigation standards found that several sections remain within ranges still considered efficient for controlled gravity-fed water transport. The fact that prehistoric builders achieved this without iron tools, modern surveying equipment, or wheeled transport remains one of the greatest mysteries of the site. Another major puzzle involves the rock-cutting techniques themselves. Many canal walls display unusually smooth surfaces and remarkably consistent edges, while some channels form near-perfect angles inside extremely hard volcanic stone. Experimental archaeologists have attempted to reproduce similar cuts using stone hammers alone. While possible on a small scale, reproducing the long continuous channels of Cumbemayo would require enormous labour and exceptional planning, with some estimates suggesting tens of thousands of hours of coordinated carving. The mystery deepens because several surfaces appear polished rather than simply broken apart. Certain grooves are so straight that they resemble marks left by controlled abrasion techniques instead of random percussion. Researchers have proposed repeated grinding using quartz-rich sand, controlled water abrasion, heating and cooling the rock to weaken fracture zones, or the use of extremely hard hammerstones transported from distant areas. None of these theories fully explain the consistency seen across the entire canal network. Comparisons are often made with the granite cutting precision of ancient Egypt, the polygonal masonry of Sacsayhuaman, and the hydraulic tunnels of Persia. Yet Cumbemayo predates many of these achievements by centuries or even millennia. One of the most controversial theories surrounding Cumbemayo is that the builders may have intentionally redirected water between different drainage systems of the Andes. The site lies close to a continental watershed divide. Water on one side eventually flows toward the Pacific Ocean, while water on the other side feeds river systems connected to the Amazon basin. Some archaeologists believe the canal may have been designed to manipulate this natural boundary. If true, this would represent one of the earliest known examples of interbasin hydraulic engineering in the Americas. Such a project would require advanced understanding of seasonal rainfall patterns, elevation changes, flow pressure, terrain mapping, and long-term erosion behavior. Even modern engineers working in mountainous terrain rely heavily on precision measurements to avoid catastrophic water instability. The idea that a prehistoric Andean culture achieved a stable transfer system more than 3,000 years ago remains deeply controversial. Satellite mapping and terrain analysis conducted in recent decades have strengthened the argument that the canal's route was carefully planned rather than naturally formed. Perhaps the most difficult mystery to explain is durability. The Andes experience intense environmental stress, including rapid temperature fluctuations, heavy seasonal rain, strong winds, and seismic activity. Under such conditions, exposed stone channels normally degrade rapidly, yet many sections of Cumbemayo remain sharply defined after 3 millennia. Hydrologists studying the site observed that several channel sections appear intentionally designed to reduce turbulence. Curved walls and controlled narrowing points may have minimized destructive water impact. In some places, the rock surfaces are smoother than surrounding natural formations, suggesting deliberate finishing methods. The durability comparison becomes even more striking when placed beside modern infrastructure. Some 20th century concrete irrigation channels in Peru have required major repairs after only a few decades of erosion exposure, while portions of Cumbemayo have survived since the late Bronze Age. This has led some researchers to argue that the builders possessed a surprisingly advanced empirical understanding of long-term hydraulic stability. Cumbemayo may not have been purely functional. Surrounding the canal system is a strange volcanic stone landscape known as Los Frailones, filled with towering rock formations shaped like human figures, animals, and pillars. Some archaeologists believe the builders intentionally integrated these natural formations into ceremonial architecture. Petroglyphs carved into nearby rocks include zigzag patterns, animal figures, abstract symbols, and flowing line motifs connected to water imagery. Several carvings are positioned directly beside canal intersections, suggesting that water itself may have held sacred meaning. Anthropologists studying early Andean belief systems note that mountain water sources were often associated with fertility, cosmic order, and divine power. At Cumbemayo, the engineering may have served both practical and religious purposes simultaneously. Acoustic studies have also produced unusual findings. Wind moving through narrow stone corridors creates resonant tones and whistling effects that some researchers think were intentionally incorporated into ceremonial experiences. This transforms Cumbemayo from a simple irrigation site into something far stranger, a fusion of engineering, landscape manipulation, and ritual design. What do you think Cumbemayo really was? An ancient engineering breakthrough far ahead of its time, or evidence that lost knowledge once existed in the Andes long before recorded history? Share your thoughts and theories in the comments below. The Nile deserts of northern Sudan hide the pyramids of Nuri far from the crowds of Giza, rising from the sand like broken black teeth. More than 80 pyramids stand here, a royal necropolis of the Kushite kingdom built over 2,500 years ago. Some are small and shattered, others still dominate the horizon despite centuries of erosion, earthquakes, floods, and looting. Yet the greatest mystery is not why they were built. It is how a civilization with far fewer resources than Egypt engineered structures and underground tomb systems so advanced that parts of them still cannot be fully explained by modern archaeology. The site was first documented in detail during the 19th century by European explorers traveling south of Egypt. Later excavations revealed that Nuri became the burial ground of Kushite kings after the reign of Taharqa, one of the most powerful rulers of Nubia and Egypt combined. Archaeologists quickly realized this was not simply a copy of Egyptian pyramid culture. The engineering methods at Nuri were different. The geometry was different. Even the underground structures followed patterns unlike those found beneath most Egyptian pyramids. At first glance, the pyramids appear smaller than those at Giza. The Great Pyramid of Khufu originally stood around 146 meters tall, while the largest pyramid at Nuri likely reached around 50 meters. But the Kushite builders compensated with steeper angles, often exceeding 70 degrees. That made construction dramatically more dangerous. In structural engineering, steeper slopes increase lateral pressure and raise the risk of collapse. Yet many pyramids at Nuri remained standing for more than 2 millennia, despite being built with less durable sandstone and rubble cores instead of massive limestone blocks like those used in Egypt. Modern engineers studying the site noticed something unusual in the foundations. Beneath several pyramids are compacted layers of crushed stone and sand acting almost like primitive shock absorbers. Similar concepts are used today in seismic base isolation systems to distribute force and reduce stress during ground movement. No written Kushite engineering manuals survive, yet the builders somehow understood how to stabilize massive structures on terrain affected by seasonal groundwater changes from the Nile. Satellite imaging and geological surveys show the underground water table around Nuri has shifted repeatedly over thousands of years. Under such conditions, most ancient mud brick structures would have fractured or sunk. Many of the Nuri pyramids did not. But the real mystery begins underground. Beneath the pyramids lie burial chambers connected by long descending stairways and tunnels cut directly into bedrock. Some passages extend more than 20 meters below the surface. Today, many are flooded by groundwater, making exploration extremely dangerous. In 2019, underwater archaeologists used scuba equipment to enter submerged chambers beneath Taharqa's pyramid. What they found raised even more questions. The tunnels were astonishingly straight. Laser measurements showed some corridors deviated only a few centimeters over long distances carved through stone. Achieving that level of alignment without modern surveying tools is extremely difficult even today. Ancient workers supposedly used bronze chisels, stone hammers, ropes, and oil lamps. Yet the geometry suggests an understanding of spatial planning far beyond what historians once assumed about Kushite engineering. Even more puzzling are the tomb ceiling systems. Several burial chambers contained massive stone blocking mechanisms designed to permanently lock the tomb after burial. Unlike simple sealed doors in many Egyptian tombs, some chambers at Nuri appear to have used sliding stone barriers hidden within narrow shafts. Archaeologists discovered grooves carved into walls where multi-ton stone slabs could descend into place with remarkable precision. In some tombs, the entrance corridors narrow sharply before widening again deeper underground, creating spaces where large blocking stones could be maneuvered and dropped into exact positions. The engineering problem is enormous. Some blocking stones likely weighed several tons. Moving them underground through confined tunnels without cranes or iron machinery would have required carefully calculated force distribution, ramps, lubrication systems, or counterweights. Yet no surviving diagrams explain how this was done. Attempts to recreate similar systems experimentally have shown that even small errors in angle or friction would jam the stones permanently before reaching their final position. What makes the mystery even stranger is the precision of the grooves themselves. In some chambers, the channels guiding the stone blocks are cut with unusually smooth surfaces and nearly symmetrical dimensions. Archaeologists comparing them with Egyptian examples noticed that certain Nuri grooves appear more mechanically refined, despite the Kushite kingdom having fewer known resources than New Kingdom Egypt. Some researchers speculate that wooden sled systems combined with wet clay lubrication may have been used. Others believe hidden sand-release chambers could have acted like primitive hydraulic braking systems, controlling the descent speed of the stones. No consensus exists. Then there is the question of labor organization. The Pyramid of Taharqa alone may have required tens of thousands of tons of stone. Transporting that amount of material across desert terrain under temperatures exceeding 40 degrees Celsius would have demanded extraordinary logistics. Ancient inscriptions suggest Kush controlled major Nile trade routes and had access to gold wealth from Nubia, but economic strength alone does not explain the engineering coordination. At Giza, archaeologists found evidence of massive worker villages, bakeries, and supply chains. Comparable infrastructure around Nuri is far less visible, suggesting the Kushites may have relied on a different and possibly more mobile labor system. The astronomical alignment of the pyramids adds another layer of mystery. Many structures face roughly north-south, but not with the exact orientation patterns used in Egyptian royal pyramids. Studies comparing stellar alignments suggest the Kushites may have used different stars as reference points, potentially adapting their system to the southern skies more visible from Nubia. Some alignments appear connected to the rising positions of specific bright stars during the Kushite era around 700 BCE. If true, the builders possessed advanced observational astronomy without leaving behind detailed written records explaining their methods. Even the stone-cutting techniques remain controversial. Certain chamber walls display parallel cutting marks so regular that some researchers initially suspected later modifications. However, dating confirms many were original. Experimental archaeology has shown bronze tools can cut sandstone effectively, but reproducing identical grooves with ancient methods requires enormous time and skill. Some cuts inside Nuri chambers are so narrow and straight that maintaining them by torchlight underground would have been extraordinarily difficult. Then came the flooding. Over centuries, rising groundwater invaded many burial chambers. Some tunnels collapsed, Others disappeared beneath dark subterranean lakes. Yet the flooding may ironically have preserved parts of the site from looters. Radar scans indicate there are still unopened voids beneath several pyramids. Entire chambers may remain untouched. That possibility has transformed Nuri into one of the most important archaeological mysteries in Africa. What do you think is still hidden beneath the flooded pyramids of Nuri? Could there still be untouched chambers waiting to reveal lost engineering secrets? Share your thoughts in the comments below. In the humid lowlands of southern Mexico, near the San Pedro Mata River in the state of Tabasco, archaeologists uncovered the remains of Moral Reforma, a forgotten Maya city hidden beneath dense jungle and flood-prone wetlands. The site was first reported in the early 20th century, but major excavations only intensified decades later when researchers realized the city was far larger and more advanced than previously believed. Each excavation season revealed something new. Massive pyramids emerged from beneath layers of vegetation. Stone monuments covered in hieroglyphs identified rulers linked to powerful Maya kingdoms such as Calakmul. Later surveys uncovered plazas, elevated platforms, drainage systems, and evidence of large-scale engineering in terrain considered extremely unstable for monumental construction. What shocked researchers most was the location itself. Moral Reforma was not built on hard mountain bedrock like many famous ancient cities. It stood in a swampy river basin with soft alluvial soil, seasonal flooding, and annual rainfall exceeding 2,000 millimeters. Modern civil engineering often struggles in such terrain without deep reinforced foundations. Yet the Maya built pyramids more than 27 meters tall here over 1,200 years ago, and many structures still remain standing. That contradiction became the beginning of one of the most overlooked engineering mysteries in the ancient Americas. The greatest mystery surrounding Moral Reforma is how its builders stabilized enormous stone structures on terrain that should have collapsed under their weight. Geological studies around the site show high concentrations of clay, saturated sediment, and flood deposits. Such soil behaves unpredictably under pressure. In modern construction, engineers usually solve this problem using deep concrete piles or steel reinforcement. The Maya had neither. Excavations beneath several ceremonial platforms revealed layered construction methods, unlike ordinary Maya foundations. Archaeologists discovered alternating levels of compacted earth, crushed limestone, gravel, and organic material carefully arranged to distribute pressure across a broader surface area. Some researchers compared the concept to modern floating foundation systems used in wetland construction today. The engineering becomes even more impressive when considering the climate. Tabasco's tropical rains rapidly erode exposed surfaces. Many colonial-era structures built only a few centuries ago in nearby regions have deteriorated more severely than the much older Maya remains at Moral Reforma. Satellite imaging and LiDAR scans suggest the city may also have been artificially elevated over time through repeated layers of engineered fill. If correct, the Maya were effectively reshaping the landscape itself to create stable urban terrain in an environment naturally hostile to permanent architecture. This raises an uncomfortable question for historians. How much practical geotechnical knowledge did the Maya truly possess? The ancient city existed in a region where water was both life and threat. Seasonal floods could transform the surrounding terrain into a vast marshland within weeks. Yet Moral Reforma survived for centuries as a major political and ceremonial center. Archaeologists later identified traces of canals, embankments, reservoirs, and raised causeways extending around the urban core. Some channels possess gradients so subtle that modern researchers initially believed they could not have functioned effectively. Yet sediment analysis indicates controlled water movement likely occurred through them for long periods. The system appears designed not only to drain floodwater, but also to regulate moisture levels across agricultural zones surrounding the city. This resembles hydraulic strategies seen at Angkor Wat in Cambodia, where vast reservoirs and canals supported dense urban populations centuries before modern hydrology. What makes moral Reforma remarkable is scale versus technology. The Maya lacked iron tools, draft animals, and wheeled transport systems for heavy labor. Despite this, they created hydraulic infrastructure sophisticated enough to sustain urban life in one of the wettest regions of Mesoamerica. Some archaeologists believe the city's survival depended entirely on this engineered landscape. If even part of the water control network failed, flooding and agricultural collapse may have followed rapidly. Ironically, the same system that allowed the city to flourish may also explain its eventual disappearance. Another major mystery concerns the movement of construction material. The region around Moral Reforma contains limited high-quality building stone, yet the city's pyramids and stairways required thousands of tons of limestone blocks. Without horses, oxen, or industrial tools, the Maya somehow transported heavy material across swampy terrain and dense rainforest. Researchers estimate some blocks weighed several tons. Moving them even short distances would have required immense coordination. One theory proposes seasonal river transport. During flood periods, stone may have been floated on large rafts through interconnected waterways before being dragged across prepared earthen ramps. Another hypothesis suggests raised causeways functioned as engineered transport corridors capable of supporting concentrated human labor teams. But none of these theories completely explain the precision of construction found at the site. Certain staircases and retaining walls exhibit alignment errors of only a few millimeters. Some joints remain remarkably tight despite centuries of rainfall and soil movement. Comparisons have been made with masonry precision at Palenque, and even with certain Andean stonework traditions thousands of kilometers away. The difference is that Moral Reforma achieved this level of stability in unstable wetland conditions, where gradual shifting should have destroyed alignment long ago. Like many Maya cities, Moral Reforma appears connected to astronomical observation. Several pyramids and plazas align closely with solar positions during equinoxes and solstices. Researchers studying the site noticed that certain ceremonial structures frame sunrise angles with unusual precision. During specific times of year, sunlight passes directly through architectural corridors and illuminates key stairways or plaza entrances. Some scholars argue these alignments were symbolic only. Others believe the city functioned partly as a giant observational instrument integrated into the Maya calendar system. The Maya already possessed one of the most accurate ancient calendars ever created, calculating solar cycles with astonishing precision centuries before European mechanical astronomy. The question is not whether the Maya understood astronomy. The real mystery is how they achieved such accuracy without optical instruments. Aligning massive structures to celestial movements requires long-term observation, mathematical consistency, and intergenerational transmission of data. At Moral Reforma, these alignments may also have served political purposes. Kings could associate themselves with predictable cosmic events, reinforcing divine authority through architecture itself. For centuries, the jungle erased nearly all memory of Moral Reforma. Then excavations uncovered carved stelae containing royal inscriptions and political records. Each discovery changed historians' understanding of the city. One monument revealed alliances with larger Maya powers. Another described military conflicts and dynastic struggles. Later inscriptions suggested the city controlled important river trade routes, linking inland kingdoms with Gulf Coast regions. This transformed Moral Reforma from a forgotten provincial settlement into a strategic political center. Yet the inscriptions also deepen the mystery. If the city possessed advanced engineering, strategic trade access, and political influence, why was it abandoned so completely? Climate change remains one possibility. Paleoclimatic studies across the Maya world indicate severe drought cycles between the 8th and 10th centuries, but moral Reforma existed in a wetland environment, making drought alone an incomplete explanation. Other researchers point toward political collapse, warfare, or failure of hydraulic infrastructure. If the water management system deteriorated, flooding could have rendered large sections of the city uninhabitable within decades. The jungle then finished what history began. In the cloud forests of northern Peru, where cold mist drifts across razor-sharp ridges of the Andes, the ancient fortress of Kuelap rises like something that should not exist. Built nearly 3,000 meters above sea level by the Chachapoya civilization centuries before the Spanish arrived in South America, Kuelap remains one of the largest and most mysterious stone complexes ever constructed in the Americas. Massive defensive walls reaching almost 20 meters in height wrap around the mountaintop like the hull of a giant stone ship. Yet the deeper archaeologists investigate the site, the stranger it becomes. Hidden among its circular buildings are unusual elevated platforms aligned with the movement of the sun, drainage systems advanced enough to survive centuries of extreme rainfall, and curved megalithic walls so geometrically consistent that modern engineers still debate how they were designed without advanced instruments. Kuelap remained largely unknown to the outside world until 1843, when the Peruvian judge Juan Crisostomo Nieto encountered the ruins while traveling through the remote Amazonas region. Later expeditions revealed an enormous fortified settlement, covering more than 6 hectares and containing over 400 circular structures. Modern LiDAR surveys and drone mapping have since uncovered additional terraces, pathways, and buried architectural features hidden beneath dense vegetation, suggesting the visible ruins may represent only part of a much larger ceremonial and defensive complex. One of the first mysteries surrounding Kuelap is the sheer impossibility of its construction. The fortress sits on a narrow limestone ridge surrounded by steep cliffs and unstable mountain terrain. Transporting stone to this altitude alone would have required an enormous labor force. Some estimates suggest the walls contain tens of thousands of metric tons of limestone blocks. Unlike later civilizations equipped with metal tools and wheeled transport, the Chachapoya had neither iron technology nor draft animals capable of hauling massive stones uphill. Even modern archaeologists climbing the site struggle to navigate the terrain carrying basic equipment. What makes the puzzle more difficult is that many stones appear partially shaped before transport. Several blocks weigh multiple tons and were positioned with remarkable stability along slopes, vulnerable to earthquakes and erosion. Engineers studying ancient logistics have compared the challenge to moving materials onto a natural aircraft carrier balanced above deep valleys. The effort required would have demanded sophisticated organization, labor management, and surveying techniques that historians once believed did not exist in this region during that period. But the greatest mystery may not be the fortress itself. It may be the strange elevated structures now referred to as the solar platforms. Scattered across certain sections of Kuelap are raised stone platforms and ceremonial spaces whose orientation appears connected to astronomical events. Archaeological measurements have shown that several alignments correspond closely with the direction of sunrise and sunset during solstices and equinoxes. Narrow stone openings allow beams of sunlight to strike specific points only during certain periods of the year. Researchers comparing the site to ancient solar observatories such as Chaco Canyon and Machu Picchu believe the Chachapoya may have incorporated astronomy directly into the city's architecture. This raises a major question. How could a civilization isolated within dense Andean cloud forests achieve such consistent, astronomical orientation without precision instruments? At Kuelap's latitude, even a slight surveying error would significantly alter the angle of solar alignment over long distances, yet some structures remain surprisingly accurate relative to the solar cycle. A few researchers suggest that Chachapoya may have tracked shadow movement across seasons for generations before construction began. Others believe the platforms were ceremonial rather than scientific, and that the alignments may partly be coincidence. The problem is that the patterns repeat too consistently across the site to dismiss entirely. The engineering mystery deepens further beneath the surface. Kuelap experiences intense seasonal rainfall capable of destabilizing mountain slopes and collapsing poorly designed foundations within decades. Yet the fortress survived for centuries. Excavations have revealed an intricate drainage network hidden under plazas and buildings, consisting of stone-lined channels, layered fill systems, and permeable surfaces designed to redirect water away from structural foundations. Archaeologists have identified hundreds of drainage openings integrated into walls and terraces. In some sectors, the builders intentionally layered stone, gravel, and compacted soil to absorb hydraulic pressure. Modern geotechnical engineers studying the fortress describe the system as astonishingly advanced for a pre-Columbian mountain settlement. Without this hidden hydraulic infrastructure, the enormous weight of the walls, combined with seasonal rainfall, would likely have triggered catastrophic landslides. Yet perhaps the most technically baffling feature of Kuelap is its colossal curved outer wall. Unlike the polygonal masonry associated with the Inca, Kuelap's defensive perimeter forms a massive continuous curve extending across uneven terrain. In certain areas, the wall rises nearly vertically, while maintaining a remarkably smooth geometric arc. Drone scans and three-dimensional reconstructions show that the curvature remains surprisingly stable over long distances, despite the irregular shape of the mountain ridge underneath. For ancient builders without modern geometry, maintaining this level of consistency should have been extraordinarily difficult. Even small deviations in curvature could have created uneven pressure distribution capable of weakening the entire structure. Instead, the wall behaves almost like a giant compression ring, redistributing weight laterally across the slope. Some sections subtly tilt inward, increasing resistance against seismic vibration and downhill force. Engineers analyzing the wall's geometry have noted similarities to later principles used in retaining structures and curved fortification systems. What makes this even stranger is the absence of clear evidence showing how the builders planned the curve. No surviving measurement tools have been discovered. There are no written records explaining the construction process, yet the wall's design implies long-distance spatial planning and a sophisticated understanding of structural load behavior. Several theories attempt to explain the precision. One proposes that the builders used ropes anchored from central reference points to maintain a stable radius while laying stone courses. Another suggests they employed wooden surveying frames, now long decayed by the humid climate. But none fully explain how the curvature remained so consistent across shifting elevations and unstable terrain. The problem becomes even more difficult considering that the walls were built centuries before European-style mathematical surveying reached the region. Inside the fortress, another mystery emerges through repetition. More than 400 circular buildings occupy the summit, yet almost none are identical. Their diameters vary according to patterns researchers still do not fully understand. Certain clusters appear arranged around elevated ceremonial zones, while others contain decorative friezes featuring diamonds, zigzags, and symbolic geometric motifs. Some archaeologists believe these patterns may have represented clan identities or social hierarchy. Others speculate they encoded astronomical or cosmological concepts linked to the solar platforms. The lack of surviving Chachapoya writing leaves these interpretations unresolved. Then, there is the atmosphere of the site itself. Kuelap is almost constantly surrounded by cloud and drifting fog. Visibility changes within minutes as sunlight cuts through the mist and vanishes again. Researchers studying the fortress have suggested that the Chachapoya intentionally exploited this environment. Certain ceremonial spaces become dramatically illuminated during sunrise while other areas disappear into shadow. From a distance, the fortress sometimes appears to float above the clouds entirely. This may explain why the site feels less like a conventional military fortress and more like a carefully orchestrated ritual landscape, where architecture, astronomy, weather, and psychology were combined into a single monumental design. The final mystery is the civilization behind it. The Chachapoya, often called the Warriors of the Clouds, constructed enormous settlements throughout northern Peru, yet much of their knowledge vanished rapidly after conquest by the Inca and later the Spanish. Unlike civilizations that left extensive written records, the Chachapoya disappeared into history with most of their engineering methods and cosmological beliefs lost forever. What do you think the builders of Kuelap truly understood? Advanced engineering, astronomy, or something we still haven't discovered yet? Share your thoughts and theories in the comments below. Eridu stands near the ancient floodplains of southern Iraq, where one of humanity's oldest and most mysterious cities emerged thousands of years before the pyramids of Egypt. Today, many archaeologists consider Eridu the first true city on Earth, and one of the greatest technological enigmas of the ancient world. Discovered through 19th and 20th century excavations led by Iraqi and British archaeologists, Eridu appeared at first to be little more than a desert mound. But beneath the sand were the remains of a civilization dating back nearly 7,000 years, older than the pyramids of Egypt and older than Stonehenge. What researchers uncovered there challenged long-held assumptions about how civilization began. For decades, historians believed cities evolved slowly from small farming villages. Eridu does not seem to follow that pattern. Archaeological layers suggest that sophisticated urban planning, large ceremonial architecture, water management systems, and organized labor emerged there surprisingly early. In many ways, Eridu appears less like the beginning of civilization and more like the remains of a society that already understood the fundamentals of engineering and centralized control. One of the greatest mysteries surrounding Eridu is its impossible location. Southern Mesopotamia was an unstable environment dominated by marshes, seasonal flooding, salt contamination, and extreme summer temperatures that can exceed 50 degrees Celsius. Even modern agriculture in southern Iraq struggles with soil salinity and water control. Yet around 5,400 BCE, the people of Eridu established a permanent settlement that survived for thousands of years. This should not have been easy. Ancient farmers faced a deadly problem in Mesopotamia. Irrigation slowly poisons the soil. As water evaporates under intense heat, salt remains trapped in the ground. Over time, farmland becomes infertile. Archaeologists studying Sumerian agriculture estimate that wheat production in some southern Mesopotamian regions eventually collapsed because salinity became uncontrollable. But Eridu endured far longer than many neighboring settlements. Excavations revealed traces of ancient canals and carefully engineered water channels surrounding the city. Some researchers believe the inhabitants developed one of humanity's earliest hydraulic management systems. The canals were not random trenches dug into mud. Their gradients appear carefully controlled, allowing water to flow while reducing stagnation and salt accumulation. A slight engineering mistake would have flooded fields or poisoned them permanently, yet the system functioned for centuries. What makes this more mysterious is the technological timeline. This was thousands of years before advanced mathematics, before iron tools, and before large surveying instruments. The people of Eridu may have relied entirely on practical experimentation, observation of seasonal water behavior, and inherited technical knowledge passed down through generations. Some archaeologists argue that southern Mesopotamian civilization was built not on military conquest, but on mastery of water engineering. At the center of Eridu stood another anomaly, a massive religious complex rebuilt again and again for millennia. Archaeologists uncovered at least 18 successive temple layers stacked directly on top of each other. Instead of demolishing older structures completely, the inhabitants preserved them beneath newer construction, gradually creating an elevated sacred platform. This process would later evolve into the famous Mesopotamian ziggurats. The strange part is the consistency. Across thousands of years, the sacred center remained aligned almost perfectly in the same location. The builders repeatedly maintained the orientation and proportions of the temple, despite different generations, political changes, and environmental shifts. Such continuity suggests the existence of a highly stable cultural or technical tradition. Some researchers speculate that early Sumerian priests may have possessed sophisticated observational systems tied to astronomy or geographic positioning. Ancient Sumerian texts later described Eridu as the city of the god Enki, deity of wisdom, water, engineering, and creation. In myth, Eridu was not merely a city, it was where divine knowledge entered the human world. To modern scholars, these legends may preserve cultural memories of a place where early technological breakthroughs transformed human society forever. But among all the mysteries of Eridu, one stands above the rest: the survival of its mud brick architecture. Most of the city was constructed using sun-dried mud bricks, one of the weakest building materials imaginable. Mud brick is vulnerable to rain, wind erosion, salt crystallization, and temperature fluctuation. Under harsh conditions, untreated mud structures can collapse within decades, yet parts of Eridu survive for nearly 7,000 years. This has become one of the most overlooked engineering mysteries in archaeology. Researchers studying ancient Mesopotamian bricks discovered that the builders of Eridu did not simply shape mud and leave it to dry. The bricks often contained carefully balanced mixtures of clay, silt, straw, reeds, and organic temper materials. These additives dramatically reduced cracking during drying and improved structural flexibility. In some samples, microscopic analysis revealed mineral compositions that helped resist salt damage, one of the greatest environmental threats in southern Iraq. The science behind this is remarkable. Straw fibers act similarly to reinforcement material in modern composite engineering. As mud dries and contracts, fibers distribute stress throughout the brick, preventing catastrophic fractures. Certain clay compositions also improve thermal stability, reducing expansion and contraction caused by brutal desert heat cycles. Modern experiments recreating ancient Mesopotamian mud bricks found that correctly mixed organic additives could increase durability several times over compared to untreated mud. But there is another layer to the mystery. Many Eridu structures were built in areas with high groundwater salinity. Salt crystals expanding inside porous materials normally destroy mud brick over time. Modern concrete itself can suffer severe degradation under similar conditions. Yet some Eridu foundations remained identifiable after thousands of years buried beneath sediment and exposed to environmental extremes. Engineers still debate how ancient builders optimized these materials so effectively without modern chemistry. Some specialists believe the people of Eridu achieved this through centuries of empirical refinement. Others argue that the consistency of the bricks suggests standardized production methods far earlier than expected in human history. Comparisons with later civilizations make the puzzle even stranger. Egyptian pyramids relied primarily on limestone and granite. Roman engineering depended heavily on volcanic ash concrete, but Eridu's builders worked with mud, arguably the least durable major construction material, and still created structures that endured across entire epochs of civilization. In terms of material survival relative to available resources, Eridu may represent one of the greatest achievements of ancient engineering. Archaeologists also uncovered evidence suggesting organized labor and centralized administration. Storage facilities, production zones, and ceremonial architecture imply a coordinated society capable of mobilizing workers on a large scale. This raises another difficult question. How was such complexity managed before writing fully developed? The earliest proto-writing systems in Mesopotamia emerged thousands of years later, yet Eridu already displayed signs of economic coordination. Some researchers believe the inhabitants used clay tokens and symbolic accounting systems to track grain, labor, and trade long before formal cuneiform writing appeared. If true, Eridu may represent the birthplace not only of cities, but also of administration itself. Trade may have played an equally important role. Southern Mesopotamia lacked many natural resources, including stone, timber, and metal ores. Yet artifacts found at Eridu suggest long-distance exchange networks connecting distant regions of the Persian Gulf and beyond. This implies that maritime travel and organized trade routes existed far earlier than once believed. Do you think Eridu was simply humanity's first city? Or evidence that ancient civilizations understood engineering far beyond what we normally imagine? Share your thoughts in the comments below. In the eastern outskirts of Lima, Peru, where modern neighborhoods press against the dry hills of the Rimac Valley, archaeologists uncovered the remains of a forgotten adobe city known as Huaca de Pariachi. At first glance, the site looked unimpressive compared to the stone fortresses of the Inca. No massive granite walls, no towering pyramids, only endless layers of eroded earth-colored structures half buried beneath dust and urban expansion. But every excavation season revealed something increasingly difficult to explain. Beneath the surface was evidence of a highly organized pre-Inca administrative center that may have mastered earthquake-resistant construction, precision urban planning, hydraulic engineering, and social control systems centuries before the Spanish ever arrived in South America. The first documented archaeological investigations around Huaca de Pariachi intensified during the 20th century as Lima rapidly expanded toward the eastern valleys. Researchers initially believed the site belonged to a relatively ordinary regional settlement of the Yixma culture, a civilization that flourished along Peru's central coast between roughly 900 and 1470 AD, before being absorbed into the Inca Empire. Early excavations exposed large plazas, corridors, storage compounds, ramps, and ceremonial compounds constructed almost entirely from adobe bricks. But the scale immediately raised questions. The site occupied a strategic position between the Andes highlands and the Pacific coast, directly connected to ancient trade corridors crossing one of the driest environments on Earth. Each new excavation revealed another layer of complexity. Archaeologists discovered extensive administrative compounds with controlled access points, narrow corridors designed to regulate movement, and massive open courtyards capable of holding large gatherings. Unlike many ceremonial centers in ancient Peru, Huaca de Pariachi appeared engineered not only for ritual activity, but also for administration, taxation, storage, and regional coordination. Some researchers compared its logistical organization to simplified forms of later Inca administrative hubs known as tampas. Yet Huaca existed before the Inca expansion fully transformed the region. One of the greatest mysteries surrounding the site is how its adobe architecture survived for centuries in one of the world's most seismically unstable regions. Peru sits directly on the Pacific Ring of Fire, where tectonic pressure from the Nazca Plate generates frequent earthquakes. Adobe construction is normally extremely vulnerable to seismic activity because dried mud bricks crack and collapse under lateral vibration. Yet many walls at Huaca de Pariachi remained standing long after abandonment. Detailed structural analysis revealed unusual engineering decisions. Some walls were extraordinarily thick at the base, but narrowed gradually upward, redistributing stress during seismic shaking. In several sectors, archaeologists identified alternating densities within adobe layers, suggesting builders intentionally varied material composition to absorb vibration. Certain internal walls also contained void-like spaces that may have functioned as primitive shock absorbers. Modern earthquake engineers studying traditional Andean construction techniques have noted similarities between these ancient methods and modern seismic damping principles used in earthquake-resistant buildings today. The mystery deepens when comparing Huaycan to other ancient adobe cities. The massive Chimu capital of Chan Chan, located farther north on Peru's coast, also relied heavily on adobe, but many of its structures suffered catastrophic erosion over time. At Huaycan, however, portions of the site retained surprising stability, despite centuries of earthquakes, seasonal humidity fluctuations, and urban encroachment. Some archaeologists suspect the builders developed specialized plaster coatings or mineral additives that slowed erosion, but the exact composition remains uncertain. Laboratory analysis has detected varying concentrations of clay, sand, shell fragments, and organic fibers within construction layers, yet no definitive formula explains the durability completely. Excavations also uncovered evidence of sophisticated water management systems hidden beneath the city's surface. This was particularly puzzling because Huayca de Pariachi sits within a hyper-arid coastal desert where annual rainfall is extremely low. Maintaining a large population in such conditions required precise control of water distribution. Researchers discovered channels, underground conduits, and carefully angled drainage systems integrated into the architecture itself. Some canal gradients were so slight that maintaining water flow would have required remarkable surveying precision. Hydraulic specialists studying the site noted that several channels appeared optimized to reduce evaporation while stabilizing sediment flow. In some sectors, layered gravel and sand beneath floors may have acted as filtration systems or moisture regulators. These discoveries fueled speculation that the inhabitants possessed a far deeper practical understanding of hydrology than previously assumed for pre-Inca coastal societies. Comparisons were drawn to ancient Persian qanat systems and Roman water engineering, though Huaycan's solutions evolved independently within a radically different environment. Another major discovery emerged from the site's unusual spatial organization. Archaeologists noticed that movement through the complex was highly controlled. Many corridors abruptly narrowed before opening into plazas. Access routes repeatedly forced sharp turns, limiting visibility and slowing large groups. Certain elevated platforms overlook central spaces with clear lines of sight over crowds below. Researchers began proposing that Huaycan functioned as a carefully engineered environment designed to reinforce hierarchy and social control. This theory gained strength when excavations uncovered evidence of restricted ceremonial sectors separated from public zones. The architecture itself appeared to dictate human behavior. In some compounds, entrances aligned in ways that directed sunlight dramatically across ritual areas during particular seasons. While not as astronomically explicit as sites like Chanquilo, the precision of alignment suggested intentional planning. Urban archaeologists compared the psychological effects of these spaces to controlled ceremonial pathways later perfected by the Inca at sites such as Huánuco Pampa. The scale of storage facilities discovered at Huaycan introduced another mystery. Excavators identified compounds that may have stored food, textiles, tribute goods, and trade commodities moving between the Andes and the coast. Yet the civilization operating this center lacked wheeled transport. Draft animals capable of carrying heavy loads over long distances, and metal tools comparable to Old World civilizations. Despite these limitations, the site appears to have supported highly organized regional logistics. Some historians now believe Huaca de Pariachi operated as a major redistribution hub, linking agricultural communities of the Rimac Valley with long-distance trade networks extending into the Andes. This would have required sophisticated administrative coordination long before the rise of the centralized Inca bureaucracy. The city's strategic location may explain why the Inca later absorbed and reused portions of the region rather than destroying them outright. Every excavation season added new questions rather than definitive answers. In some areas, archaeologists discovered traces of repainting and architectural modification spanning multiple generations, suggesting continuous adaptation of the site over centuries. Elsewhere, buried structures indicated that older ceremonial sectors were intentionally sealed beneath newer construction phases, hinting at changing political or religious systems. Several sectors remain unexcavated today, buried beneath both desert sediment and the expanding urban sprawl of modern Lima. What do you think the builders of Huaca de Pariachi truly understood about earthquakes, water, and engineering that may have been lost to history? Share your thoughts in the comments below. Perched dramatically on a sheer cliff nearly 900 meters above the Paro Valley, the legendary Paro Taktsang, widely known as the Tiger's Nest Monastery, stands as one of the most breathtaking and enigmatic architectural achievements in the Himalayan world. Suspended against a vertical wall of granite at an altitude of more than 3,000 meters above sea level, the monastery appears almost unreal, as if it were placed there by forces beyond ordinary human capability. From a distance, the complex seems to grow directly out of the mountain itself, its whitewashed walls and golden roofs clinging to the cliff face with astonishing precision. While the site is revered as one of the holiest places in Bhutanese Buddhism, it also presents a series of engineering puzzles that continue to fascinate historians, architects, and scientists. The question that repeatedly arises is simple yet profound. How was such a structure built in a location that even today is extraordinarily difficult to access, and what construction techniques allowed it to remain stable on such an unforgiving landscape for centuries? The origins of the site are closely connected to the Buddhist master Padmasambhava, who, according to Bhutanese tradition, arrived at this cliff in the 8th century and meditated in a cave within the rock face. Legend describes him flying to the site on the back of a tigress, an image that later gave the monastery its famous name, Tiger's Nest. For centuries, the cave remained a sacred pilgrimage destination, but the monastery complex that now surrounds it was formally constructed in 1692 under the direction of the Bhutanese religious leader Tenzin Rabgye. Even within the historical record of Bhutan, however, the details of the construction process remain remarkably scarce. There are no surviving architectural plans, no detailed written accounts describing the building stages, and almost no physical evidence of the large-scale infrastructure that must have been required to assemble such a complex in this extreme environment. As a result, the monastery exists today not only as a sacred monument, but also as a fascinating technical mystery. One of the most obvious challenges lies in the location itself. The cliff on which Paro Taktsang stands is nearly vertical, rising sharply above dense forest and deep valleys carved by Himalayan rivers. Even today, visitors must travel along a steep mountain trail for hours to reach the monastery, and large equipment cannot easily be transported to the site. Yet the original builders somehow managed to carry enormous quantities of timber, stone, roofing materials, clay plaster, statues, and ceremonial objects to this impossible height. The logistics alone would have required extraordinary coordination and physical endurance. Scholars have suggested that ropes, wooden scaffolding, and pulley systems may have been used, perhaps anchored to higher points along the cliff face. Others believe temporary pathways or carved ledges may once have existed along the rock. However, almost no physical remains of such construction systems have survived, leaving researchers to reconstruct the process largely through speculation. The difficulty of transporting materials up such a dangerous cliff raises an even more intriguing question. Once the materials arrived, how were they actually secured to the mountain? This question leads directly to one of the most mysterious technical aspects of the entire complex: the hidden system of foundations and structural anchors that hold the monastery against the rock face. Unlike many buildings constructed on mountain slopes, Paro-Taktsang does not simply rest on a stable plateau or wide terrace. Instead, large portions of the structure appear to be suspended directly above steep drops, supported by narrow ledges, protruding rock shelves, or cavities carved into the granite. In some places, the monastery walls rise directly from the cliff, as though the stone itself had been shaped to receive them. The visible architecture suggests that the builders integrated the monastery deeply into the natural geometry of the rock, carefully adapting each building to the irregular contours of the cliff. Yet the true engineering behind this integration remains difficult to observe, because much of the structural support is hidden within the rock itself. Researchers believe that ancient builders may have drilled deep holes into the granite and inserted massive wooden beams that functioned as anchors, effectively tying the monastery to the mountain. These beams would then support floors, balconies, and external galleries projecting outward from the cliff. Such techniques were not entirely unknown in Himalayan architecture, but the scale and precision required at Tiger's Nest appear far more advanced than typical examples. What makes the mystery even deeper is the relative absence of visible drilling marks on many sections of the rock. If large anchoring beams were inserted into the cliff, the holes used to place them should still be identifiable in at least some areas, yet many surveys of the site have revealed surprisingly few traces of large-scale drilling or chiseling. This absence of clear evidence has led some researchers to suggest that the builders may have used natural fissures and cavities within the rock itself, carefully inserting structural elements into existing weaknesses in the stone rather than carving new ones. If this hypothesis is correct, it would imply an extraordinary understanding of the geological structure of the cliff, as the builders would have needed to identify stable fracture lines, capable of supporting heavy loads. Another possibility involves the strategic use of stone platforms built directly onto the rock ledges, distributing weight across multiple contact points, rather than relying on a single foundation. By spreading structural load across several smaller surfaces, the monastery could remain stable even on narrow projections of stone. Modern structural engineers who have examined similar techniques note that such load distribution can significantly reduce the stress placed on any single point of support. However, applying this principle on a nearly vertical cliff with limited access would have required exceptional planning and craftsmanship. Every beam, wall, and support would need to be precisely aligned with the irregular surfaces of the mountain, ensuring that the building remained balanced despite strong winds, seismic activity, and centuries of erosion. The materials used in the construction of Paro-Taktsang also reflect a remarkable adaptation to the harsh Himalayan climate. The monastery combines timber frames with stone foundations and thick layers of clay-based plaster, forming a structure that can expand and contract with temperature fluctuations while maintaining structural stability. Wooden beams allow for slight flexibility during earthquakes, a crucial feature in a seismically active region such as the Himalayas. At the same time, the stone components anchor the buildings firmly to the cliff. This combination of rigidity and flexibility may explain how the monastery has survived numerous environmental stresses over the centuries. The region regularly experiences powerful mountain winds, dramatic shifts in temperature between day and night, and seasonal monsoon rains that can destabilize weaker structures. Yet Tiger's Nest continues to stand. Its buildings balance between gravity and stone in a way that appears almost miraculous. Historical records indicate that the monastery has endured fires and natural disasters, including a major blaze in 1998 that destroyed several parts of the complex. Despite the damage, the fundamental structural system anchored to the cliff remained intact, allowing reconstruction efforts to rebuild the damaged sections using traditional Bhutanese architectural techniques. This resilience further highlights the effectiveness of the original engineering principles, even if those principles are not yet fully understood. For modern engineers, the monastery represents a fascinating example of how traditional construction knowledge can achieve stability in environments that would challenge even contemporary building technology. Ultimately, the mystery of Parotaktsang lies not only in its dramatic location, but in the hidden engineering knowledge within its structure. Ancient builders managed to anchor an entire monastery to a vertical cliff without modern surveying tools, cranes, or reinforced concrete. Even today, as visitors stand on the narrow balconies overlooking the Paro Valley, one question remains. How did the original builders create a foundation system strong enough to grip the living rock itself? Until clearer archaeological evidence is discovered, Tiger's Nest will continue to stand as both a sacred sanctuary and a remarkable monument to ancient engineering whose secrets remain only partly understood. How do you think ancient builders managed to anchor an entire monastery to a nearly vertical cliff like this? Share your thoughts or theories in the comments below. Perched on a near-vertical rock fortress in the plains of Pamphylia, Silion was a city that somehow mastered water, stone, and survival, hundreds of meters above the ground long before modern engineering existed. Located about 30 kilometers northeast of modern Antalya in southern Turkey, Silion was known in ancient Greek and Roman records for centuries, but systematic archaeological surveys only intensified during the 19th and 20th centuries as researchers began mapping the hidden ruins spread across the mountain summit. The first mystery of Silion is simple. Why build an entire city on top of an isolated stone mountain nearly 300 meters high? Unlike many ancient settlements that formed around rivers or fertile valleys, Silion sits on a steep rocky plateau with almost no natural advantages except defense. The cliffs surrounding the city are so steep that ancient historians described it as nearly impossible to conquer. Even armies moving through Anatolia during the campaigns of Alexander the Great reportedly avoided direct assaults on heavily fortified mountain cities like this, because the cost of attacking them was enormous. But defense alone does not explain the engineering challenge. To construct Silion, ancient builders had to transport thousands of tons of stone, timber, tools, and food supplies uphill across rough terrain, without cranes, engines, or steel machinery. Some retaining walls still standing today contain massive stone blocks fitted with unusual precision. In several sections, the gaps between stones remain incredibly tight despite nearly 2,000 years of earthquakes, erosion, and weathering. Researchers often compare this style of tight polygonal masonry to sites such as Sacsayhuaman or Machu Picchu, because the stones appear carefully shaped to distribute force across uneven surfaces. While Silion was built by a completely different civilization, the underlying engineering principle appears strangely similar. Structures designed to survive instability, by allowing energy to spread through interlocking geometry rather than rigid straight lines. That detail becomes even more shocking when considering the seismic activity of Anatolia. Southern Turkey sits near active tectonic zones, meaning these walls endured repeated ground movement for centuries. Yet parts of the city still remain attached to the cliff face with remarkable stability. The greatest unsolved engineering puzzle of Silion is not its walls or theatre. It is water. Ancient cities survive or die based on water access, and Silion should never have survived at all. The mountain summit contains no major natural spring capable of supporting a large urban population. Yet archaeological surveys uncovered enormous cisterns carved directly into bedrock, underground reservoirs, drainage tunnels, and sophisticated channels designed to collect and preserve rainwater with extraordinary efficiency. Some cisterns are estimated to hold hundreds of cubic meters of water. That alone is impressive, but the real mystery is precision. Water systems in ancient cities depended entirely on gravity. If a channel descended too steeply, flowing water would erode the stone and destroy the structure. If the angle was too shallow, water would stagnate or fail to move entirely. Modern hydraulic engineering uses laser measurement systems and advanced surveying equipment to calculate these gradients. The builders of Silion had none of these technologies, yet many surviving channels maintain slopes accurate enough to keep water moving steadily across difficult rocky terrain. This has led some researchers to compare Silion's hydraulic planning to the Nabatean systems of Petra. In Petra, engineers controlled flash floods and redirected water across desert cliffs with gradients so precise that modern studies found deviations sometimes measured only in millimeters per meter. Silion appears to show a similar understanding of hydraulic balance. The city's engineers also seem to understand long-term water preservation. Several reservoirs were coated internally with waterproof plaster mixtures containing lime compounds and crushed ceramics, materials known to improve resistance against leakage and bacterial growth. Roman hydraulic concrete using volcanic ash was famous for durability, but Silion's mountain cisterns reveal that regional engineers may have adapted comparable methods using locally available minerals. Even more fascinating is the possibility that the city operated as a giant rain harvesting machine. The mountain's steep slopes naturally accelerated runoff during storms. Instead of allowing water to escape downhill, channels redirected it into storage chambers throughout the city. This means Silion's survival may have depended not on a river, but on carefully engineered control of seasonal rainfall. That level of planning required advanced surveying, precise stone cutting, understanding of pressure and flow, and long-term urban resource management. In other words, this was not primitive engineering, it was systems engineering. Beneath parts of Silion are underground chambers and carved passageways, whose full extent remains unclear. Some tunnels likely served military purposes, allowing defenders to move supplies or access hidden storage areas during sieges, but several carved surfaces raise uncomfortable questions for archaeologists. Some sections display unusually flat cuts and sharp internal angles carved directly into limestone. Reproducing those surfaces using only basic bronze tools would have been extremely slow. Iron tools were available later, but the consistency of certain cuts suggests highly organized labor and surprisingly advanced stoneworking methods. Experimental archaeologists have proposed multiple explanations, including heating rock with fire and rapidly cooling it to fracture surfaces, wooden wedges soaked in water to expand inside cracks, hardened iron chisels, or abrasive sand cutting techniques. Yet none fully explain the speed required to shape an entire fortified mountain city. At sites throughout the ancient world, difficult stonework repeatedly appears in places where civilizations faced extreme environmental challenges. The Incas shaped earthquake-resistant stone walls in Peru. The Nabateans carved entire structures into sandstone cliffs. The Romans drilled tunnels through mountains for aqueducts. Silion belongs in that same category of ancient engineering that feels disturbingly advanced for its era. The remains of Silion's theatre reveal another technical mystery: acoustics. Ancient theatres across the Greek and Roman world were famous for amplifying sound naturally, but Silion's elevated location may have enhanced this effect even further. The curved seating arrangement, combined with reflective stone surfaces and the surrounding cliff geometry, created an unusually effective resonance chamber. Modern acoustic studies at ancient theatres show that certain designs amplified speech frequencies between roughly 500 and 4,000 Hz, the exact range most important for human vocal clarity. Builders clearly understood through experimentation that geometry could manipulate sound. At Silion, the mountain itself may have functioned as part of the acoustic design. If intentional, this suggests the city's architects possessed sophisticated empirical knowledge of wave reflection centuries before the formal science of acoustics existed. Ancient records describe Silion as extraordinarily difficult to capture. From the summit, defenders could monitor movement across much of the Pamphylian plain and nearby trade routes connected to the Mediterranean coast. This strategic advantage transformed the city into more than a settlement. It became a surveillance platform, military fortress, and emergency refuge combined into one. The mountain's steep sides acted like natural defensive walls. Attackers climbing uphill would exhaust themselves long before reaching the gates, while defenders above maintained visibility in every direction. Combined with large water reserves and internal storage systems, Silion may have been capable of surviving sieges for extended periods. That raises another mystery. If the city was so defensible, why was it eventually abandoned? What do you think really caused the fall of Silion? Earthquakes, water failure, or something historians still have not discovered? Share your thoughts in the comments below. The ancient Toltec city of Tula, about 70 kilometers northwest of modern Mexico City, is home to the Atlantean columns standing atop Pyramid B like silent mechanical guardians from another age. Each figure rises nearly 4.6 meters tall, weighs several tons, and was carved from hard volcanic basalt nearly 1,000 years ago. What makes them extraordinary is not only their size, but the engineering questions they continue to raise. Archaeologists still debate how the Toltecs, between the 10th and 12th centuries, transported, assembled, and balanced these massive stone warriors on the summit of a pyramid without metal cranes, wheeled transport systems, or large draft animals. Even today, many of the technical methods behind their construction remain uncertain. The first modern rediscovery of Tula began during the 19th century when explorers traveling through central Mexico reported enormous buried stone fragments scattered across the site. Early excavations uncovered sections of giant carved limbs and torsos, but no one initially understood they belonged to complete standing figures. In the 1940s, Mexican archaeologist Jorge Ruffier Acosta conducted more systematic excavations around Pyramid B. As layers of debris were removed, researchers realized the fragments formed 4 colossal warrior statues placed on the pyramid's summit. This discovery immediately changed the understanding of Toltec architecture. Instead of decorative sculpture alone, the figures appear to function as structural columns supporting the roof of a temple complex above them. Further excavations revealed something even more surprising. The Atlantean columns were not carved from single monolithic blocks. Each warrior was assembled from multiple precisely shaped basalt sections stacked vertically with remarkable alignment accuracy. The head, torso, legs, and lower base were engineered to interlock, while distributing enormous vertical weight. Modern structural analysis suggests that even slight misalignment in the load distribution could have caused cracking at the neck or waist over centuries of stress. Yet the statues survived earthquakes, erosion, and nearly a millennium of exposure. Some engineers comparing ancient stone structures note that this level of vertical balance resembles certain load-bearing calculations seen in much later Roman and medieval stone architecture. The basalt itself deepens the mystery. Basalt ranks around 6 on the Mohs hardness scale, making it extremely difficult to carve using primitive stone tools. Experimental archaeology shows that shaping volcanic basalt with simple hammerstones can require hundreds of labor hours even for relatively small surfaces. Yet the Atlantean columns contain highly detailed carvings of butterfly-shaped chest plates, feather ornaments, ceremonial knives, and atlatl dart throwers. The symmetry of these engravings suggests planned measurement systems rather than improvised carving. Some researchers believe the Toltecs may have used abrasive cutting techniques involving quartz sand and water, functioning almost like a primitive industrial grinding process. Similar theories have been proposed for hard stone cutting in ancient Egypt and at Ollantaytambo, where precise stonework also appears beyond what traditional tools alone would easily explain. One of the greatest unanswered questions involves transportation. Geological studies indicate the basalt likely originated several kilometers from the pyramid complex. Transporting blocks weighing multiple tons across uneven terrain and then lifting them more than 10 meters above ground level would have required a massive coordinated labor system. Unlike Eurasian civilizations, the Toltecs lacked oxen, horses, or functional transport wheels for heavy hauling. Some archaeologists suggest giant earthen ramps combined with wooden rollers and agave fiber ropes. However, no complete transport infrastructure has ever been found at Tula. This mirrors similar unresolved engineering puzzles at Baalbek, where stones exceeding 800 tons were somehow moved into position nearly 2,000 years ago. Another discovery at the site revealed that the Atlantean columns were aligned with a carefully planned ceremonial axis across the city. Their positioning on Pyramid B faces specific directions associated with solar movement and ritual processions. Some archaeoastronomers argue that the orientation may connect to the cycle of Venus, a celestial body deeply associated with warfare and divine rulership in Mesoamerican cultures. Venus held enormous symbolic importance among the Maya and Toltecs because its appearance patterns could be predicted with surprising accuracy. Codices from later civilizations recorded Venus cycles with errors of only a few hours across many years. The possibility that the Atlantean columns were integrated into astronomical observation systems suggests the structure may have served both ceremonial and scientific purposes simultaneously. As excavation continued through the 20th century, researchers uncovered evidence that the statues once supported a large roofed temple complex. Stone sockets and beam placements indicate the figures acted as actual architectural columns carrying substantial overhead loads. This discovery shocked many historians because humanoid load-bearing sculptures on this scale are extremely rare in pre-Columbian America. The closest comparisons often come from caryatid columns in ancient Greek architecture, yet the Toltec examples developed independently on another continent centuries later. Some structural historians believe the Atlantean columns represent one of the most advanced integrations of symbolic art and engineering in the ancient Americas. The warrior imagery itself also raises questions about Toltec military technology. The figures carry atlatls, specialized spear-throwing devices capable of dramatically increasing projectile velocity. Experimental reconstructions show that atlatl darts can exceed 150 km per hour and penetrate armor or animal hide with devastating force. This suggests the Toltecs possessed advanced practical knowledge of leverage, kinetic force, and aerodynamic efficiency long before formal physics existed. Some scholars argue that the exaggerated depiction of military equipment on the statues may symbolize elite warrior orders controlling both political and religious authority inside Tula. Chemical analysis of surviving pigment traces has revealed that the statues were once brightly painted in red, blue, black and white mineral-based colors. This means the grey stone appearance seen today is only a weathered remnant of their original form. Reconstructed models suggest the temple summit would have appeared visually overwhelming under sunlight, with towering painted warriors visible from large distances across the city. The psychological effect may have been intentional, functioning as a display of state power similar to colossal imperial monuments in ancient Egypt or Assyria. Despite decades of study, major mysteries remain unresolved. No surviving Toltec texts explain the construction process. No tools capable of producing the finest basalt detailing have been definitively identified. Archaeologists still debate whether the statues were carved directly near the pyramid or transported as partially finished components. The exact methods used to stabilize the figures against seismic movement are also uncertain. Modern laser scans reveal surprisingly precise proportional consistency among the statues, implying standardized measurement systems that are still poorly understood. What do you think the Toltecs truly knew about engineering and stone construction nearly 1,000 years ago? Could the Atlantean columns represent lost building techniques that modern researchers still do not fully understand? Share your thoughts and theories in the comments below. Along the northern shores of the Black Sea, on the Kerch Peninsula of present-day Crimea, lie the quiet ruins of an ancient harbour that once connected distant worlds. Known today as the Nymphaion harbour complex, this coastal installation formed the maritime heart of the ancient Greek city of Nymphaion, a colony established around the 6th century BCE by settlers from the Ionian Greek world. At first glance, the site appears modest, scattered stones along a sloping coastline overlooking a calm inlet. Yet beneath this seemingly simple landscape lies a maritime system that once played a critical role in the trade networks of the northern Black Sea. Archaeological research over the past century has revealed that Nymphaion was not merely a provincial outpost, but a strategically positioned harbour capable of supporting large volumes of maritime commerce. Even more intriguing are the questions that remain unanswered. How ancient engineers selected such an ideal natural harbour, how its stone structures were built and maintained in a dynamic marine environment, and perhaps most mysteriously, why this once important port gradually disappeared from the historical stage. The geographic setting of Nymphaion immediately explains part of its ancient importance. The harbour was situated in a naturally protected bay, where the coastline bends inward, forming a sheltered inlet guarded by rocky outcrops and gentle slopes of land. In antiquity, this natural protection would have shielded ships from the powerful winds and waves that often sweep across the Black Sea. Ancient mariners valued such locations immensely, because safe anchorage meant the difference between reliable trade and constant danger. Geological studies of the bay indicate that the seabed here offered a rare combination of stability and depth. Unlike many coastal zones that accumulate shifting sandbanks, the waters of Nymphaion appear to have maintained a relatively consistent depth suitable for merchant vessels. This raises an intriguing possibility. The founders of the settlement may have possessed a surprisingly detailed understanding of local maritime conditions. Choosing such an ideal harbour location suggests that early Greek colonists carefully surveyed the coastline rather than selecting the site randomly. Archaeological excavations have revealed that the natural harbour was enhanced with human engineering. Remains of stone quay structures and possible breakwaters indicate that ancient builders modified the shoreline to create organized docking areas for ships. Large stone blocks were carefully arranged to stabilize the waterfront, forming platforms where cargo could be loaded and unloaded. The stones themselves show evidence of deliberate shaping and placement, suggesting that construction required planning and coordinated labor. Working in a coastal environment is notoriously difficult even with modern technology, yet the builders of Nymphaion managed to establish durable structures along the edge of an active sea. These constructions likely served multiple purposes. Some segments may have functioned as protective barriers that reduced wave impact, while others formed docking points where ships could be tied securely. The arrangement implies that the harbour was designed to support regular commercial traffic rather than occasional visits. Further evidence of organised maritime activity appears in the form of carved anchor holes and mooring points discovered along the stone installations. These features suggest that ships could be secured directly to the harbour infrastructure, allowing crews to stabilise their vessels during loading operations. Historical sources indicate that Nymphaion played a significant role in exporting grain from the fertile steppe regions north of the Black Sea. Vast agricultural lands produced surplus grain that was transported by river and land routes to coastal ports, where it could then be shipped across the sea to Greek cities. Among the most important destinations was Athens, whose growing population depended heavily on imported grain. Nymphaion therefore became part of a larger economic network linking the northern frontier of the Greek world with the major urban centres of the Mediterranean. Yet the harbour complex still holds physical mysteries. Underwater surveys conducted in recent decades have identified submerged stone features near the ancient shoreline. Some of these structures appear to be remnants of harbour walls or docking platforms that are now partially buried beneath sediments. Their positions do not always correspond neatly with the present coastline, leading researchers to suspect that the ancient shoreline may have shifted over the centuries. Changes in sea level, coastal erosion, or sediment accumulation could have gradually altered the configuration of the harbour. If this is correct, the original port facilities may once have extended farther into the bay than they appear today. The underwater remains hint at a larger and more complex harbour system that has only partially survived the passage of time. Despite these impressive features, the greatest mystery surrounding the Nymphaion harbour complex lies not in its construction but in its disappearance. For centuries, the harbour functioned as an active node within the Bosporan kingdom, a powerful regional state that controlled trade routes around the Cimmerian Bosporus. Ships arrived with merchants, amphorae, grain cargo, and travellers moving between the Greek world and the vast interior of Eurasia. Archaeological layers confirm that the city prospered during this period, supported by maritime exchange and agricultural exports. But gradually, the rhythm of trade that sustained Nymphaion began to weaken. By the later centuries of antiquity, signs of decline become increasingly visible in the archaeological record. Harbour installations appear to have fallen into disrepair, and fewer imported goods are found in the settlement layers. Historians have proposed several possible explanations for this transformation. One theory suggests that shifting trade routes reduced the strategic importance of the port. As political centres and economic networks changed, merchants may have begun favouring other coastal hubs that offered better protection or more direct connections to emerging markets. Another possibility involves environmental change. If sediment gradually accumulated within the harbour basin, it could have reduced the depth of the water and made docking increasingly difficult for larger ships. Even small changes in water depth can transform a once reliable harbour into a risky anchorage. Political instability may also have played a role. The Bosporan kingdom experienced periods of internal conflict and external pressure from neighbouring powers. Military disruptions often had immediate consequences for trade. especially in frontier regions where maritime commerce depended on security and stable governance. A port such as Nymphaion, positioned along a critical maritime corridor, would have been particularly vulnerable to these shifts in political power. If regional authority weakened, merchants might have redirected their routes towards safer ports. Yet none of these explanations fully accounts for the gradual fading of the harbour from historical prominence. Unlike cities that were destroyed suddenly by war or natural disaster, Nymphaion appears to have declined slowly, almost quietly. The harbour didn't vanish overnight, rather its activity diminished generation by generation. Cargo shipments decreased, maintenance of harbour structures ceased, and eventually the once busy docks fell silent. Over time, the sea and the land reclaimed the infrastructure that had supported centuries of maritime exchange. Today, the remnants of the Nymphaion harbour complex lie scattered along the coastline, their stones weathered by wind and salt. What remains is only a fragment of the ancient system that once operated here. Yet these ruins preserve a powerful reminder of how interconnected the ancient world truly was. A harbour built by Greek colonists on the distant shores of the Black Sea could feed populations thousands of kilometres away and sustain economic relationships across continents. And still, the ultimate fate of this port remains an open question. Was its decline caused by environmental change, shifting trade networks, political instability, or a combination of all three? The evidence continues to invite investigation. In this sense, the silence of the harbour is itself part of the mystery. The stones of Nymphaion reveal that ancient engineers understood their maritime environment well enough to construct a functional port in a remote frontier region. They built quays, organised docking systems, and integrated the harbour into a vast network of trade. But history rarely preserves the final chapter of such places. As the centuries passed, the ships stopped coming, the harbour installations eroded, and the once vital gateway of Nymphaion slowly disappeared into the landscape, leaving behind only fragments of stone and a puzzle that archaeologists are still trying to solve. In your opinion, what truly caused Nymphaion harbour to gradually disappear from history? Environmental changes, shifting trade routes, political instability, or perhaps another factor we have yet to uncover? Share your thoughts in the comments below. Within the rugged mountains of northern Algeria, near the region of Kabylie, the ancient Kabylie settlements were never meant to become one of North Africa's strangest archaeological mysteries. Many of these mountain cities were first systematically documented during French colonial surveys in the 19th century, though local Berber communities had occupied the region for centuries before modern archaeology arrived. What shocked researchers was not simply the age of the settlements, but their engineering. Entire communities had been constructed on steep mountain slopes where modern urban planners would struggle to build even today. Some villages sit more than 800 meters above sea level, surrounded by unstable rock formations, seismic activity, and harsh seasonal weather. Yet many of their structures remain standing after hundreds, possibly over 1,000 years. Satellite terrain analysis later revealed something even stranger. The settlements were not randomly positioned. Many occupied mathematically advantageous ridges with optimal visibility, defensive geometry, and natural water capture potential. Archaeologists began comparing them to Inca mountain cities in Peru, particularly Machu Picchu. Despite being separated by an ocean and developing independently, the deeper researchers looked, the more difficult it became to explain how isolated mountain communities without advanced machinery achieved such precision. One of the greatest mysteries surrounding the ancient Kabylie cities is how they were physically constructed on terrain that should have made large-scale architecture nearly impossible. Many structures were built using dry stone masonry, a technique where stones are fitted together without mortar. But unlike ordinary stone stacking, Kabil walls often display interlocking geometry that distributes pressure evenly across the structure. Some walls lean inward at carefully calculated angles, increasing resistance against earthquakes and slope collapse. Modern engineers studying ancient mountain architecture found similarities between Kabil construction and anti-seismic systems used by the Incas. In both cases, flexibility appears to have been intentionally engineered into the stonework. During ground vibration, the walls can absorb movement rather than crack instantly. What makes this difficult to explain is the technological context. The Kabil mountain communities did not possess advanced iron industries comparable to Rome. Archaeological finds mostly include primitive iron tools, stone hammers, and simple chisels. Yet some stone joints are so precise that inserting even a thin metal blade between blocks is nearly impossible. Geologists also discovered that many foundations were built directly into mountain bedrock, using carved anchoring channels. This significantly reduced landslide risk. Similar stabilization methods are used today in modern mountain engineering projects worth millions of dollars. The question remains, how did ancient builders without surveying lasers, cranes, or reinforced concrete achieve such long-term structural stability? Perhaps the most scientifically puzzling aspect of the Kabil settlements is their water management system. Northern Algeria experiences highly irregular rainfall. Summers are dry, temperatures can exceed 35 degrees Celsius, and mountain evaporation rates are intense. Yet archaeological evidence suggests that some Kabil settlements supported surprisingly dense populations for centuries. Researchers discovered underground cisterns, sloped drainage systems, and narrow hydraulic channels carved directly into stone. Several channels maintain gradients so precise that water could travel long distances without eroding the system itself. Hydraulic engineers examining these ruins noted that some slopes appear intentionally optimized to control water velocity. If water moved too quickly, erosion would destroy the channels. Too slowly, and sediment would clog them. The surviving system suggests an advanced empirical understanding of fluid dynamics. Even more mysterious are traces of waterproofing compounds inside certain reservoirs. Chemical analysis detected mixtures containing clay, ash, lime, and silica-rich minerals. The formula resembles waterproof Roman hydraulic concrete in several functional ways, despite developing in geographically isolated mountain communities. Some reservoirs also maintain unusually cool temperatures internally, reducing evaporation. Researchers suspect the builders may have intentionally used subterranean airflow and thermal stone properties to create passive cooling systems. In a region where water determined survival, the Kabil hydraulic systems appear far more sophisticated than historians once believed possible. Another unexplained feature is the strategic positioning of the settlements themselves. From many ancient Kabil locations, observers can see neighboring mountain ridges dozens of kilometers away. Digital topographic reconstruction has shown that numerous sites maintain nearly uninterrupted lines of sight with one another. This has led researchers to believe the Kabil communities may have operated a long-distance communication network using smoke, fire, reflective surfaces, or signal beacons. The precision is remarkable. Without satellite imagery or aerial mapping, the builders somehow selected positions that maximized both visibility and defensibility simultaneously. Some alignments show only minimal angular deviation despite the extremely difficult terrain. Military historians compare the system to Byzantine beacon chains and sections of the Great Wall signal towers in China. But unlike imperial states with centralized engineering institutions, the Kabil settlements were decentralized mountain communities. This raises an uncomfortable historical question. Were these societies far more technologically organized than traditional history suggests? The mountains of Kabylie are not naturally suited for large-scale agriculture. Soil erosion is severe, flat land is limited, and seasonal rainfall is inconsistent. Yet ancient terraces built by Kabil communities still survive today. Many terraces were constructed using retaining walls designed to slow water runoff while trapping nutrient-rich sediment. Modern environmental engineers studying the region found that some terrace systems dramatically reduce erosion even after centuries of exposure. Several ancient agricultural zones also contain unexpectedly fertile soil layers. Chemical studies suggest long-term artificial enrichment using ash, decomposed organic material, and mineral-rich sediment. In effect, the Kabil may have engineered sustainable mountain soil centuries before modern ecological agriculture. The terraces also create microclimates. Stone walls absorb heat during the day and release it slowly at night, reducing sudden temperature fluctuations that damage crops. Similar principles are now used in climate-adaptive agriculture. What remains unclear is how mountain communities with limited written records accumulated such advanced environmental knowledge over generations. Unlike many ancient civilizations that disappeared after conquest, Kabil culture endured through waves of foreign empires including Phoenician, Roman, Byzantine, Arab, Ottoman, and French expansion. What fascinates historians is that many indigenous engineering traditions survived despite these occupations. Anthropologists believe this may indicate an unusually efficient oral knowledge system. Construction techniques, water management strategies, and agricultural methods appear to have been transmitted across generations without extensive written documentation. This parallels other highly resilient mountain civilizations such as communities in the Andes or Himalayas, where isolation protected technical traditions for centuries. But in the Kabil case, the survival is even more surprising because North Africa experienced repeated military invasions and political upheaval over 2,000 years. Despite this, many mountain settlements preserved architectural identities unlike Roman or Arab urban models. Do you think the ancient Kabil civilization possessed engineering knowledge far beyond what historians currently believe? Share your thoughts and theories in the comments below. Dumat al-Jandal sits in the al-Jawf region of northern Saudi Arabia, near one of the few major groundwater zones in the harsh Nafud desert system. Archaeologists had known the oasis for centuries through Assyrian inscriptions dating back to the 7th century BCE, where it appeared as Ad-Dummatu, a fortified desert stronghold controlling caravan routes between Mesopotamia and the Arabian Peninsula. But modern excavations accelerated only in the 20th century, when aerial surveys and satellite imagery revealed that the visible ruins represented only a fraction of a much larger buried settlement. Early excavations uncovered stone fortifications, ancient wells, religious structures, and layers of occupation stretching across more than 2,000 years. Each excavation season revealed something unexpected: underground water channels, imported ceramics from the Levant and Mesopotamia, Nabatean-style masonry, and architectural alignments that appeared too deliberate to be random. What began as a desert ruin slowly transformed into one of the most mysterious ancient engineering sites in Arabia. The first major mystery surrounding Dumat al-Jandal is simple. How did a large urban settlement survive for centuries in one of the driest environments in the Middle East? Average annual rainfall in the region is extremely low, often below 60 millimeters per year. Daytime temperatures can exceed 45 degrees Celsius, while nighttime temperatures may drop dramatically within hours. Such thermal stress normally destroys ancient stone structures over long periods, yet Dumat al-Jandal endured. Excavations revealed dozens of ancient wells carved deep into sandstone and limestone layers. Some remain functional even today. Hydrogeologists studying the oasis discovered that many wells were positioned with unusual precision along natural fracture systems connected to underground aquifers. This suggests that ancient builders possessed advanced empirical knowledge of desert hydrology long before formal geological science existed. Researchers comparing the oasis to settlements in Petra and Palmyra notice similarities in water management strategy but important differences in execution. Petra relied heavily on carved channels and cistern systems. Dumat al-Jandal instead appears to have depended on groundwater extraction, combined with controlled distribution through smaller concealed channels. Some archaeologists believe evaporation reduction techniques may have been used, though physical evidence remains incomplete because many structures collapsed centuries ago. The engineering puzzle becomes even stranger when population estimates are considered. Some studies suggest the oasis may have supported several thousand inhabitants at its peak, in addition to passing caravan networks. Maintaining enough water for agriculture, animals, and trade caravans would have required logistical coordination comparable to much larger ancient cities. Above the oasis rises Marid Castle, a fortress dominating the surrounding desert landscape. Local tradition claims the structure is impossible to conquer, and its design partially explains why. The fortress was constructed directly onto uneven rocky terrain using massive stone blocks fitted into the natural contours of the hill. Engineers studying the surviving walls observed that many sections remained stable despite centuries of erosion, earthquakes, thermal expansion, and desert winds carrying abrasive sand particles. One unresolved mystery is the apparent absence of extensive mortar use in certain sections. Similar to some Nabatean and even Incan construction techniques, many stones appear to rely primarily on geometric interlocking and weight distribution. Precision fitting reduced structural movement while allowing limited expansion under temperature changes. Modern structural simulations indicate that this flexibility may have helped the fortress survive environmental stress better than rigid masonry systems. Yet researchers still debate how ancient builders achieved such accurate stone placement on steep terrain without advanced lifting equipment. The mystery deepened after laser scanning surveys detected hidden interior chambers and blocked passageways beneath some walls. Several remain unexplored because excavation risks destabilizing parts of the structure. Some archaeologists suspect these hidden sections may contain older construction phases predating the visible fortress entirely. Among the most debated discoveries at Dumat al-Jandal are its ancient religious structures and their possible astronomical alignments. Archaeologists identified several pre-Islamic sacred areas oriented along unusually consistent directional axes. Measurements showed that some walls and entrances aligned closely with solar positions during seasonal transitions, particularly sunrise and sunset near solstices and equinoxes. The statistical probability of multiple structures sharing similar astronomical orientations purely by accident is relatively low. This has led researchers to propose that ancient inhabitants intentionally incorporated celestial observations into architectural planning. What makes the mystery more complex is the precision involved. In some cases, alignment errors are only a few degrees despite the absence of documented surveying instruments. Ancient Arabian societies are known to have relied heavily on astronomy for navigation across open desert terrain, but Dumat al-Jandal suggests something more systematic may have existed. Comparisons have been made to Nabatean solar alignments at Petra, and even to certain Egyptian temple orientations, though on a smaller scale. However, unlike Egypt or Mesopotamia, northern Arabian civilizations left behind far fewer written technical records explaining how such measurements were achieved. One theory proposes that generations of observers tracked shadow movements over decades using simple marker stones. Another suggests that caravan trade exposed local engineers to astronomical knowledge from Mesopotamia, where Babylonian sky observation was already highly advanced by the first millennium BCE, yet no consensus exists. Some alignments appear intentional. Others may simply reflect practical environmental planning, such as optimizing shade and airflow. The problem is that both explanations may be true simultaneously, making it difficult to separate engineering necessity from symbolic cosmology. Recent archaeological surveys uncovered evidence suggesting that Dumat al-Jandal's builders may have manipulated airflow and thermal behavior inside parts of the city. Several storage structures contain unusually thick walls, combined with narrow ventilation openings positioned at calculated angles. Thermal modelling performed on surviving foundations suggests interior temperatures could have remained 8 to 12 degrees Celsius cooler than outside desert conditions. This resembles passive cooling strategies seen in Persian windcatcher systems centuries later. Though Dumat al-Jandal predates many of those technologies, researchers still do not fully understand how airflow circulated through the structures because upper architectural sections have largely disappeared. However, traces of internal channels imply that some buildings may have functioned as primitive climate control systems using pressure differentials between shaded and exposed surfaces. If confirmed, this would represent one of the earliest sophisticated passive cooling adaptations discovered in northern Arabia. Dumat al-Jandal occupied a strategic position linking Mesopotamia, the Levant and Central Arabia. Excavations uncovered imported ceramics, glass fragments, incense residues, and metal goods, originating hundreds or even thousands of kilometers away. This raises another unresolved question. How did ancient trade caravans reliably navigate and survive such extreme desert distances? Modern logistics experts studying ancient caravan systems estimate that large camel caravans required enormous water coordination. A single camel can consume more than 100 liters of water after prolonged dehydration. Supporting large-scale trade routes would have required carefully planned oasis intervals and highly reliable water reserves. Some researchers believe Dumat al-Jandal may have possessed hidden underground storage systems not yet discovered. Ground-penetrating radar surveys continue revealing buried anomalies beneath the oasis, suggesting substantial unexplored infrastructure still exists below the modern archaeological zone. What do you think is still buried beneath the sands of Dumat al-Jandal? Lost technology, forgotten civilizations, or something even more mysterious? Share your thoughts in the comments below. Perched high above the rugged landscape of southern France, the fortress known as Château de Quéribus appears less like a conventional castle and more like a natural extension of the mountain itself. Rising dramatically from a narrow limestone peak in the Corbières range, the citadel stands at an altitude of more than 700 meters above sea level, dominating the surrounding valleys and distant plains. From afar, the structure seems almost impossible. Stone walls clinging to the summit of a jagged rock formation, exposed to wind, weather, and gravity for centuries. Historians often refer to Quéribus as one of the legendary citadels of the sky, a group of nearly inaccessible mountain fortresses that once marked the frontier between medieval France and the Kingdom of Aragon. Yet beyond its dramatic location and strategic importance, the castle also raises a series of intriguing questions about the technical knowledge and construction methods of the people who built and expanded it during the Middle Ages. The origins of Quéribus remain partly obscured by time. Historical references suggest that a fortress may have existed on the site as early as the 10th century, though the structure visible today largely dates to the 13th century, when the region became entangled in the turbulent history of the Cathar movement and the Albigensian Crusade. For a time, the castle served as one of the final strongholds of the Cathars, a Christian sect declared heretical by the Catholic Church. After the fall of nearby fortresses, Quéribus reportedly held out until the middle of the 13th century before eventually coming under royal control. The French crown then reinforced and modified the structure, transforming it into a border fortress that guarded the frontier with Spain for several centuries. Although its political role gradually diminished after the Treaty of the Pyrenees shifted the border southward, the architectural complexity and remarkable engineering of the site continue to attract historians, archaeologists, and engineers who seek to understand how such a structure could be built in such an extreme location. One of the first mysteries surrounding Quéribus concerns the sheer difficulty of its construction site. The castle stands on a razor-thin ridge of limestone that drops steeply on several sides, leaving very little flat ground on which to build. Transporting building materials to such a height would have been a formidable task in the medieval world. Every block of stone, every beam of timber, every barrel of mortar had to be carried up winding mountain paths long before modern roads or machinery existed. Some researchers believe that builders quarried much of the stone directly from the mountain itself, shaping the fortress out of the very rock on which it stands. Others suggest that a system of wooden cranes, pulleys and scaffolding may have been used to lift materials upward in stages. Whatever the precise method, the logistics alone would have required careful planning, coordination, and an understanding of structural balance that challenges common assumptions about medieval engineering capabilities. The defensive design of the fortress reveals another level of sophistication. Rather than imposing a rigid geometric layout onto the mountain, the builders shaped the walls to follow the irregular contours of the rock. The result is a structure that blends almost seamlessly with its natural foundation, as if the mountain itself had grown defensive towers and stone ramparts. Access routes were intentionally narrow and winding, forcing anyone approaching the castle to move slowly through a sequence of gates, stairways, and courtyards that could be easily defended. Such features reflect a deep understanding of topography and military strategy. By integrating architecture with the natural terrain, the designers effectively turned the entire mountain into part of the fortress, maximizing defensive strength while minimizing the need for massive artificial walls. Inside the castle, the most striking architectural space is the Great Hall located within the main tower. This chamber contains a central stone pillar from which 4 Gothic arches radiate outward to support the vaulted ceiling. The elegance of this structure is remarkable, considering the limited tools available to medieval builders. Each stone block forming the arches had to be cut with precise angles, so that the weight of the roof would distribute evenly through the pillar and into the rock below. The geometry required for such a vault is complex, relying on carefully calculated curves and load-bearing lines. When viewed from below, the arches appear almost effortless, yet they represent a sophisticated understanding of structural mechanics that would have been developed through generations of practical experience. Perhaps the most intriguing technical mystery of Quéribus lies in the stonework itself, particularly in the traces left behind by the tools used to shape the blocks. Many of the stones forming the fortress walls display cutting marks that are strikingly consistent across large surfaces. The grooves and planes appear remarkably straight, with edges that meet at sharp angles and surfaces that remain unusually smooth despite centuries of exposure. For archaeologists examining these details, the stonework raises important questions about the technology available to medieval masons. Conventional historical explanations suggest that craftsmen used iron chisels, hammerstones, and wedges to split and shape limestone blocks. These tools were certainly capable of producing well-finished masonry, yet the level of uniformity observed in some sections of Quéribus suggests a degree of control that seems surprisingly advanced for the era. The precision becomes especially noticeable when examining joints between adjacent stones. In several areas of the fortress, the blocks fit together so tightly that very little mortar is visible between them. The surfaces appear to have been carefully flattened so that each stone rests securely against its neighbour, distributing weight evenly throughout the wall. Achieving this level of accuracy would have required repeated measuring, trimming, and testing of each block before it was finally placed. Even a small misalignment could weaken the stability of the structure, especially in a fortress perched on a narrow summit exposed to strong winds. The builders, therefore, had to balance speed, precision, and structural safety while working under challenging environmental conditions. some researchers have proposed that the masons working at Quéribus may have inherited techniques passed down from earlier Roman or Mediterranean stone-cutting traditions. Others believe the precision reflects the high level of craftsmanship achieved by specialized guilds of medieval builders who traveled from project to project across Europe. Regardless of the explanation, the stonework demonstrates a mastery of material that continues to fascinate modern observers. When sunlight strikes the pale limestone walls, the subtle tool marks become visible, revealing the rhythm of countless hammer blows delivered centuries ago by craftsmen whose names have long been forgotten. The durability of the fortress further deepens the mystery. Despite standing atop an exposed mountain ridge for more than 700 years, Quéribus remains remarkably intact. Its walls have endured relentless winds, storms, and temperature changes that would normally erode poorly constructed structures. The tight fit of the stone blocks, combined with the natural strength of the limestone and the stability of the underlying bedrock, appears to have created a building capable of resisting the forces of nature for centuries. In many ways, the fortress demonstrates how effective medieval engineering could be when combined with careful observation of natural conditions. Today, as visitors climb the steep path to the summit, the fortress still inspires awe. From the top, sweeping views stretch across the valleys of the Ord region, while the stone walls seem to rise naturally from the mountain itself. Beyond the dramatic scenery lies a deeper story of ingenuity, perseverance, and technical skill. The precisely cut stones, elegant Gothic vaults, and the seamless integration of architecture with the rocky peak suggest that the builders of Château de Quéribus possessed remarkable engineering knowledge. More than a medieval fortress, Quéribus stands as a testament to the craftsmanship of the masons who shaped each block by hand, high above the valleys of southern France. Their work transformed a jagged mountain peak into one of Europe's most striking fortresses, one that still leaves historians questioning the exact techniques and tools that made such precision possible. In your opinion, how were medieval builders able to cut and fit stone blocks with such remarkable precision on a steep mountain peak? Share your thoughts in the comments below. Carved between mountains, marshes, and the sea, Kaunos may contain some of the most technically impossible cliff tombs of the ancient world. Rising directly from vertical rock walls above the Dalyan River in southwestern Turkey, these massive stone facades were built more than 2,000 years ago with a level of precision that still confuses engineers today. The ruins of Kaunos were known locally for centuries, but systematic archaeological investigation began in the 19th century and expanded dramatically under Turkish excavations in the 1960s. What researchers uncovered was not simply a forgotten Greco-Roman city, but a highly advanced urban system positioned in one of the most unstable environments imaginable. Beneath layers of sediment and clapped stone were theatres, baths, hydraulic systems, temples, harbours, and the famous Lycian-style cliff tombs that turned Kaunos into one of the greatest archaeological enigmas of Anatolia. One of the strangest mysteries surrounding Kaunos is geographical. Today the city sits several kilometers inland, surrounded by wetlands and reeds. Yet, in antiquity, Kaunos was a major Mediterranean port directly connected to the sea. Geological studies of the Dalyan Delta show that sediment carried by the Dalyan River gradually filled the harbour basin over centuries. Researchers estimate that thousands of tons of silt accumulated annually, slowly transforming navigable water into marshland. Ancient writers, including Strabo, described Kaunos as a prosperous harbour city, yet modern visitors see no coastline nearby. What shocks many archaeologists is evidence suggesting the inhabitants understood the silting process and repeatedly attempted to fight it. Excavations indicate the harbour was modified multiple times through dredging, retaining walls, and artificial channels designed to redirect water flow. Maintaining a functional harbour in such a high sediment environment would have required constant engineering intervention. Modern comparisons make this even more impressive. Similar sediment problems forced repeated large-scale dredging projects in ports like Alexandria and Venice using industrial technology, yet Kaunos attempted to solve comparable hydrological challenges over 2 millennia ago using primitive tools. Some researchers believe the city may have possessed surprisingly sophisticated observational knowledge of river behavior, erosion, and water currents. Although there is no evidence of formal hydraulic science, the scale of intervention suggests empirical engineering far beyond what is typically associated with regional Anatolian cities of the period. The most famous structures of Kaunos are its monumental rock-cut tombs, carved directly into nearly vertical cliffs overlooking the river valley. At first glance, they resemble ordinary temple facades, but the deeper researchers examine them, the stranger they become. Several tombs stand dozens of meters above the valley floor, in positions that remain extremely difficult to access even with modern climbing equipment. Their entrances are framed by perfectly symmetrical columns, geometric pediments, and flat-cut surfaces carved into unstable limestone cliffs. In some places, the stone was removed with such precision that deviation between opposite sides measures only a few centimeters despite the enormous scale. The question is simple. How did ancient workers create this level of symmetry on sheer vertical rock faces without modern scaffolding systems? The dominant theory suggests massive wooden platforms were anchored directly into the cliffside. However, almost no physical evidence of these support systems has survived. Some archaeologists argue that temporary beam sockets visible in the rock may indicate suspended working platforms, but reconstructing such structures reveals staggering logistical problems. To carve a facade 10 to 15 meters high, workers would have needed stable, load-bearing scaffolding, advanced rope systems, coordinated teams operating at dangerous heights, accurate measurement methods, and long-term structural planning. Even more mysterious is the consistency of proportions between multiple tombs. Researchers comparing the facades discovered repeated geometric ratios that imply standardized measurement systems. Certain column widths and spacing patterns appear mathematically controlled rather than improvised. This becomes remarkable when compared with many other rock-cut necropolises of the ancient world. At sites where carving occurred under less difficult conditions, asymmetry and uneven finishing are common, yet the Kaunos tombs maintain unusually balanced geometry despite their extreme location. Some engineers studying the site propose that ancient builders may have used suspended plumbline systems combined with horizontal reference grids carved directly into the stone before excavation began. Others suggest they may have worked from top to bottom, gradually lowering platforms as carving progressed. But no explanation fully resolves how such high precision was achieved repeatedly on unstable vertical surfaces. The mystery deepens further when considering erosion. The limestone cliffs have endured earthquakes, rain, temperature fluctuations, and wind exposure for over 2,000 years, yet many structural details remain recognizable. This suggests the builders intentionally selected portions of rock with specific density and fracture characteristics, implying geological knowledge gained through long-term experience. Even today, reconstructing these tombs using only period-accurate tools would be an enormous challenge. Kaunos existed beside marshlands notorious for insects and disease. Ancient sources repeatedly mention unhealthy air and severe malaria outbreaks in the region. Yet, despite these environmental dangers, the city developed into a major urban centre, capable of supporting large populations for centuries. archaeologists discovered evidence of surprisingly advanced hydraulic planning beneath the ruins. Stone drainage channels were constructed with carefully calculated gradients that allowed water to flow continuously without destructive erosion. Public baths incorporated circulation systems designed to remove wastewater efficiently, while some residential zones appear intentionally elevated above the wettest areas of the valley. Researchers studying the drainage angles found that several channels maintained highly effective slopes remarkably similar to modern gravity-based water systems. Without laser measurement tools or modern surveying instruments, achieving these gradients would have required precise practical engineering. The city also appears to have separated clean water distribution from waste disposal in certain sectors. This level of sanitation planning was uncommon outside the largest Roman urban centres. Some historians argue Kaunos may represent an overlooked example of ancient environmental adaptation, where generations of builders gradually learned how to survive within an unstable swamp ecosystem through engineering rather than relocation. The theatre of Kaunos rises against the hillside with seating for thousands of spectators. What fascinates acoustic researchers is how effectively sound still travels through the structure today. The geometry of the seating rows, the angle of elevation, and the curvature of the performance area appear intentionally optimized for voice projection. Similar studies conducted in Epidaurus and other classical theatres demonstrated that ancient architects could manipulate reflected sound waves with astonishing effectiveness. At Kaunos, even whispers from the lower stage can sometimes be heard far above depending on atmospheric conditions. This suggests the builders possessed extensive empirical understanding of acoustics long before the mathematical physics of sound existed. The phenomenon likely emerged through generations of experimentation, but the precision involved continues to impress modern engineers. Inside several cliff tombs, archaeologists found burial chambers where carvings and surfaces survived unusually well, despite centuries of exposure. This raised an important question. Were the tombs intentionally designed to regulate humidity and airflow? Some chambers contain narrow ventilation gaps almost invisible from the exterior. These openings may have reduced moisture accumulation while stabilizing internal temperature. Similar passive airflow principles are used in some modern preservation architecture. If intentional, the design suggests ancient builders understood practical microclimate management through observation rather than formal science. The preservation conditions become even more surprising considering the humid marsh environment surrounding Kaunos. Organic decay, salt exposure, and moisture should have accelerated deterioration significantly. Perhaps the greatest mystery of Kaunos is that the city survived at all. Surrounded by steep mountains, marshlands, disease, and constant sediment buildup, Kaunos should have been an extremely difficult place to build a major settlement. Yet it remained an important trading center for centuries through engineering solutions such as water control, reinforced infrastructure, and continuous urban redesign. Rather than conquering nature, Kaunos reveals how an ancient civilization adapted to a hostile environment through practical engineering and observation. A few kilometers north of Jericho, one of the hottest inhabited regions on Earth, the ruins of Hisham's palace hide technology that should not exist in an 8th century desert palace. Beneath collapsed stone walls lie advanced heated floors, earthquake-resistant foundations, hydraulic engineering, and one of the most mathematically precise mosaics ever discovered from the early Islamic world. Even after more than 1,300 years of earthquakes, extreme heat, and erosion, parts of the palace still preserve details so accurate that laser scans struggle to explain how they were achieved using only hand tools. The ruins were first seriously investigated in the 1930s by archaeologists from the British Mandate Department of Antiquities. Excavations revealed that the site covered nearly 60 hectares, making it one of the largest Umayyad desert palace complexes ever discovered. What stunned archaeologists was not only the scale, but the sophistication. The palace contained bathhouses, underground heating systems, water channels, decorative marble, carved stucco, and an enormous mosaic floor, unlike almost anything found in the region. Many researchers initially believed parts of the structure were later additions, because several engineering techniques seemed too advanced for the early 8th century. Later, dating confirmed most of the complex belonged to the Umayyad period, likely constructed during the reign of Caliph Hisham ibn Abd al-Malik around 740 CE. Then came the larger mystery. The palace appears to have been abruptly abandoned after the devastating earthquake of 749 CE, freezing the site in time. The most famous mystery inside Hisham's palace is the legendary Tree of Life mosaic. Covering roughly 825 square meters, it is considered one of the largest and finest mosaics ever found in the Middle East. At first glance, the mosaic appears decorative, but modern analysis revealed something far stranger. The artwork contains over 1 million tesserae, tiny stone cubes often measuring less than 1 centimeter across. Researchers using digital mapping found that many curved sections maintain remarkably consistent angular symmetry over long distances. In several areas, deviation from intended geometric alignment is less than 2 millimeters across multiple meters of surface. That level of consistency is difficult even with modern guidelines and measuring equipment. Yet the mosaic builders achieved it using primitive tools, natural pigments, and hand-cut stone. The central image itself is deeply symbolic. A tree flanked by peaceful gazelles on one side and a lion attacking prey on the other. Historians interpret it as a representation of peace and power, but some researchers focus more on the engineering than the symbolism. The tesserae were cut from limestone, marble, and coloured minerals transported from different regions. Red stones likely contained iron oxides, while darker tones may have used manganese-rich minerals. Several pigments still remain vivid after more than 13 centuries despite Jericho's harsh climate, where summer temperatures regularly exceed 40 degrees Celsius. Material scientists studying surviving sections discovered evidence that some stones may have undergone controlled heating before placement to stabilize coloration and reduce weathering. If correct, this suggests the builders possessed practical knowledge of thermal mineral treatment centuries before similar documented methods became common elsewhere. Even more mysterious is the layout precision. To maintain alignment over such a massive floor, workers would have needed accurate reference grids and long-distance measurement systems. Yet no surviving measuring instruments from the site explain how this was done. Comparisons with Roman mosaics from places like Pompeii show that while Roman artists achieved extraordinary detail, the geometric regularity at Hisham's palace rivals some of the finest late imperial examples, despite being built in a very different political and economic environment. Some archaeologists believe the palace inherited lost Byzantine engineering traditions. Others argue the Umayyads had already developed their own highly organized mathematical construction systems. The truth remains uncertain. Hidden below the palace is another astonishing technological mystery, a hypocaust heating system similar to those used in elite Roman bathhouses. Underneath the floors, rows of small brick pillars supported elevated stone surfaces while hot air circulated beneath them. This allowed rooms to be heated evenly from below, essentially an ancient form of central heating. The engineering challenge was enormous. If airflow tunnels were uneven by even a small margin, heat distribution would fail. Yet thermal studies of reconstructed sections suggest the system maintained surprisingly balanced heat flow. Researchers also found evidence that some floor materials were specifically designed to withstand repeated thermal expansion and contraction. Certain mortar samples contained silica-rich compounds and volcanic ash components similar to pozzolanic mixtures used in Roman concrete. The strange part is geography. Jericho is nowhere near major volcanic regions. Transporting volcanic material across such distances would have required expensive trade networks and deliberate engineering choices. This implies the builders intentionally selected specialized materials for heat resistance rather than simply using locally available resources. Several engineers comparing the palace to Roman bath complexes noted similarities in thermal efficiency. But the palace was constructed centuries after the decline of Western Roman authority, raising difficult questions about how such technical knowledge survived and spread across the region. The palace sits near the Jordan Rift Valley, one of the most seismically active regions in the Middle East. The earthquake of 749 CE devastated cities across the Levant, including parts of Jerusalem, Tiberias, and Jericho. Yet some sections of Hisham's palace survived unexpectedly well. Structural analysis revealed unusual construction techniques inside certain walls. Instead of using purely solid masonry, builders alternated stone layers with softer internal materials capable of absorbing vibration. Several foundations also contained layered gravel and compacted soil systems that may have functioned as primitive shock absorbers. Modern seismic engineers have compared the concept to methods later observed in Byzantine architecture and even certain Inca structures in Peru. Whether this design was intentional remains debated. But if deliberate, it suggests the builders understood practical seismic behavior through observation and accumulated experience long before modern geology existed. The unsettling implication is that ancient engineers may have possessed far more empirical knowledge about earthquakes than surviving written records indicate. Water management at the palace remains another unresolved mystery. Jericho receives very limited rainfall, yet the complex included baths, fountains, ornamental pools, and irrigation systems requiring continuous water flow. Archaeologists discovered narrow channels built with extremely subtle gradients to maintain natural pressure and movement. In some areas, slope variation is so slight that errors of only a few centimeters could have disrupted the entire system. Researchers studying surviving plaster coatings identified waterproof compounds made from lime, ash, and crushed ceramics. Similar hydraulic plasters were used in Roman ports and cisterns because they resisted cracking and mineral leakage. The larger question is sustainability. Climate reconstruction suggests maintaining such a luxurious hydraulic system in the 8th century may have required far more water than local springs alone could reliably provide during dry periods. This has led some historians to suspect the existence of a much larger regional water distribution network that has not yet been fully uncovered. What do you think the builders of Hisham's palace really knew about engineering and mathematics over 13 centuries ago? Share your thoughts and theories in the comments below. Rising abruptly from the vast emptiness of the Yolistan Desert in Pakistan, Derawar Fort appears less like a typical desert fortress and more like a colossal architectural statement carved into the horizon. Surrounded by endless dunes and scorching winds, the fortress dominates the landscape with its massive circular bastions and towering defensive walls that seem almost improbable in such an unforgiving environment. From a distance, the structure resembles a monumental ring of red-brown stone rising out of the desert sands, its sheer scale immediately raising questions about how such a fortress could have been built, supplied, and maintained in one of the harshest regions of South Asia. Historically associated with the rulers of the region and expanded during later dynasties, the fortress stands today not only as a relic of political power, but also as a silent testimony to engineering capabilities that continue to puzzle historians, archaeologists, and architectural researchers. At the core of its mystery lies the enormous logistical challenge of constructing such a massive fortification deep within the desert. Derawar Fort stretches for roughly 1.5 kilometers around its perimeter and is reinforced by 40 immense circular bastions that rise dramatically above the surrounding sand. Each bastion appears designed not merely as a decorative element, but as a carefully calculated defensive structure, allowing defenders to monitor the surrounding landscape from multiple angles and eliminate blind spots along the walls. Yet the true puzzle lies not only in the defensive strategy, but in the practical realities of building the fortress in the first place. Millions of bricks would have been required to erect walls of such thickness and height, and each brick needed clay, water, and an immense amount of heat for firing. In the middle of the Sholistan Desert, where vegetation is scarce and fuel sources are limited, the question of how these bricks were produced at such scale becomes a profound mystery. If they were fired locally, vast quantities of fuel must have been transported or harvested from distant regions, requiring an organized supply network that would have been astonishing for its time. If they were transported from elsewhere, the logistical effort of moving so many heavy materials across desert terrain would have required a complex system of caravans, laborers, and possibly animals, coordinated with remarkable efficiency. Equally intriguing is the strategic placement of the fortress on slightly elevated terrain, often described as a citadel hill within the otherwise flat desert environment. Even a modest elevation in such an open landscape would dramatically improve visibility, allowing guards to detect approaching caravans or armies from many kilometers away. This position also suggests that Derawar Fort may have served not merely as a defensive structure, but as a key node along ancient trade routes that once crossed the desert between Central Asia, Persia, and the Indian subcontinent. Merchants traveling through the region may have relied on fortified outposts like this one for protection, taxation points, or supply stops, turning the fortress into both a military installation and an economic checkpoint. However, archaeological evidence about the exact nature of these trade networks remains incomplete, leaving historians to reconstruct the fortress's role through scattered historical references and the clues preserved in its architecture. Among all the mysteries surrounding Derawar Fort, perhaps the most astonishing is the extraordinary durability of the materials used in its construction. The fortress walls, built largely from fired brick and bonded with ancient mortar, have endured centuries of relentless desert conditions that would normally erode lesser structures. The Kholistan Desert is not a gentle environment for architecture. Temperatures can soar to extreme levels during the day and drop significantly at night, creating constant cycles of thermal expansion and contraction. Powerful desert winds carry fine sand particles that gradually grind away exposed surfaces, and occasional seasonal rains can introduce moisture that weakens poorly made materials. Yet despite these challenges, large portions of Derawar Fort's walls remain standing with remarkable stability, their massive bastions still towering over the desert as they did generations ago. This resilience has drawn the attention of engineers and material scientists who seek to understand how the fortress's construction materials have resisted degradation for so long. The fired bricks themselves appear to possess unusual density and strength, suggesting that the ancient brick makers achieved exceptionally high firing temperatures or used carefully selected clay mixtures that produced more durable building units. Even more intriguing is the mortar that binds these bricks together. In many places, the mortar joints remain firmly intact despite centuries of environmental stress. Some researchers suspect that the mortar may contain a sophisticated mixture of lime, mineral ash, and organic additives that enhanced its bonding strength and resistance to weathering. Similar techniques were used in other ancient civilizations, such as the Romans, whose volcanic ash-based concrete famously hardened over time and became stronger when exposed to certain environmental conditions. Whether the builders of Derawar Fort independently developed a comparable formula or inherited construction traditions from earlier regional cultures remains an open question. Chemical analyses of surviving mortar samples have revealed complex mineral compositions, but the precise recipe used by the original builders has yet to be fully reconstructed. The possibility that ancient engineers possess specialized knowledge of materials science, knowledge that was gradually lost or transformed over the centuries, adds another layer of fascination to the study of the fortress. Architectural evidence also suggests that Derawar Fort was not constructed in a single phase, but evolved through multiple stages of expansion and reinforcement. Variations in brick size, mortar composition, and wall thickness indicate that different rulers may have modified or strengthened the fortress over time, adapting it to changing military technologies and political circumstances. As artillery weapons became more prominent in regional warfare, thicker and more resilient walls would have been necessary to withstand bombardment. Some bastions appear to have been reinforced or rebuilt during later periods, demonstrating an ongoing process of architectural adaptation. Yet even these modifications seem to have respected the original structural principles that gave the fortress its durability. The survival of Derawar Fort across centuries of environmental exposure, political upheaval, and partial abandonment raises a profound question about the nature of ancient engineering knowledge. Modern construction often relies on advanced machinery and standardized industrial materials, yet many contemporary structures struggle to endure even a fraction of the time that ancient monuments have survived. The builders of Derawar Fort, working with comparatively simple tools and technologies, managed to create a structure capable of resisting desert winds, shifting sands, and extreme temperatures for hundreds of years. Their understanding of materials, geometry, and structural stability must have been far more sophisticated than historical records alone might suggest. Today, Derawar Fort stands as both a historic landmark and a lasting architectural mystery. Its towering bastions stretch across the desert skyline, reminding visitors that ancient engineering achievements often surpass modern expectations. More than a relic of regional power, the fortress reflects remarkable human ingenuity in an extreme environment. The unusual durability of its materials continues to puzzle scientists trying to recreate ancient construction methods, ensuring that Derawar Fort remains one of the most fascinating architectural enigmas of South Asia. What do you think is the greatest mystery of Derawar Fort? The extraordinary durability of its construction materials, the engineering required to build it in the middle of the desert, or the possibility that ancient technical knowledge has been lost? Share your thoughts in the comments below. Rising from the rugged basalt cliffs of western India, the monument known today as the Ellora Kailasa, or the Kailasa Temple of Ellora, stands as one of the most astonishing achievements of ancient engineering and artistic vision. Located within the vast rock-cut complex of Ellora in Maharashtra, this temple is unlike almost any other structure on Earth. Instead of being assembled from blocks of stone, it was carved directly from a single massive rock formation. Entire halls, towers, courtyards, stairways, and sculptural galleries were meticulously excavated from the mountain itself. The result is not merely a temple, but an entire architectural complex hewn from one continuous piece of stone. For archaeologists, historians, and engineers alike, the Ellora Kailasa represents a masterpiece that raises profound questions about the technical knowledge and organizational capacity of the civilization that created it. Most scholars believe the temple was commissioned during the 8th century under the rule of King Krishna I of the Rashtrakuta dynasty. Yet even with this historical framework, many aspects of its construction remain deeply mysterious. The builders did not create the temple in the conventional manner of ancient architecture, where structures are erected layer by layer from the ground upward. Instead, the Ellora Kailasa was carved from the top of the cliff downward. This approach required extraordinary planning. Once workers began cutting into the rock, there was little room for error. A miscalculation in the layout of the temple or its supporting pillars could have compromised the entire structure. Despite this challenge, the temple's geometry, proportions, and spatial organization reveal a level of architectural foresight that continues to astonish modern researchers. The scale of the excavation itself is staggering. Archaeologists estimate that between 200,000 and 400,000 tons of basalt rock were removed to create the temple complex. Even using modern machinery, the removal of such a vast quantity of stone would be a significant undertaking. Yet the builders of Kailasa accomplished this task using only ancient tools and methods. Historical records suggest that the temple may have been completed within only a few decades. If those estimates are correct, the workforce would have had to remove massive amounts of stone every single day. This has led some scholars to question whether we fully understand the methods and organizational systems employed by the ancient craftsmen responsible for the project. Beyond its remarkable construction process, the architectural layout of the Ellora Kailasa is itself an extraordinary achievement. The temple complex includes a monumental central shrine dedicated to the Hindu god Shiva, surrounded by subsidiary shrines, pillared halls, gateways, courtyards, and towering sculptural facades. Massive stone elephants appear to support the base of the structure, giving the impression that the entire temple rests upon a procession of carved animals. Multi-story galleries overlook the central courtyard, and long corridors lined with pillars create a sense of rhythm and symmetry throughout the complex. What makes this arrangement even more astonishing is the fact that every column, stairway, and architectural element was carved from the same continuous rock formation. Yet perhaps the most breathtaking aspect of the Ellora Kailasa, and the feature that most clearly demonstrates the artistic brilliance of its creators, is the extraordinary quality of its sculptural decoration. The temple is covered with an immense program of carvings that transform the stone surfaces into a vast narrative landscape of myth, symbolism, and sacred storytelling. Walls, pillars, ceilings, and exterior facades are adorned with intricately detailed reliefs depicting scenes from Hindu mythology, particularly the epic traditions of the Ramayana and the Mahabharata. These carvings are not merely decorative additions to the architecture. They are fully integrated into the design of the monument, forming a seamless fusion of sculpture and structure. The precision and depth of these carvings are remarkable. Many reliefs contain multiple layers of figures arranged in dynamic compositions that convey movement, emotion, and dramatic tension. Deities, warriors, celestial beings, and mythological creatures emerge from the stone with astonishing clarity. In some scenes, the sculptors created complex overlapping figures that give the impression of depth, almost as if the stone itself were unfolding into 3 dimensions. The surfaces of the sculptures were carefully polished and shaped to capture subtle variations in light and shadow, allowing the images to appear vivid even in the dim interior spaces of the temple. One of the most famous sculptural panels within the complex depicts the mythological episode of Ravana shaking Mount Kailash. In this dramatic scene, the powerful demon king Ravana attempts to lift the sacred mountain of Shiva, causing the entire cosmic landscape to tremble. The relief captures the intensity of the moment with extraordinary skill. Ravana's muscular form strains beneath the weight of the mountain, while the divine figures above remain poised in calm authority. The composition demonstrates a deep understanding of anatomy, movement, and narrative expression. What makes this achievement even more remarkable is that the sculptors were working directly into the living rock of the mountain. Each line and contour had to be carved with precision, as mistakes could not easily be corrected. Throughout the temple complex, similar masterpieces appear in countless variations. Pillars are wrapped in ornate patterns, and figures that spiral upward toward elaborately carved capitals. Walls contain vast storytelling panels in which entire mythological episodes unfold across the stone surface. Some carvings are so finely detailed that individual strands of hair, delicate jewellery, and intricate fabric patterns can still be recognised more than 1,000 years after their creation. The consistency of quality across such a vast number of sculptures suggests the presence of highly skilled workshops working under a unified artistic vision. The mystery surrounding these carvings lies not only in their beauty, but also in the tools and techniques required to produce them. Basalt is an extremely hard volcanic rock, making it difficult to carve even with modern equipment. Yet the artisans of Ellora were able to shape it into smooth surfaces, sharp edges, and delicate ornamental details. Archaeologists have found limited evidence of the specific tools used, and while iron chisels were likely involved, the exact processes by which such refined surfaces were achieved remain a subject of debate. Another intriguing aspect of the Ellora Kailasa is the apparent harmony between engineering and artistic design. The sculptural program does not appear to have been added after the structure was completed. Instead, the carvings seem to have been planned from the very beginning, integrated into the architectural framework as the excavation progressed. This suggests that the builders possessed a comprehensive vision of the entire monument long before the first section of rock was removed. Such coordination between architecture and sculpture would have required careful planning, detailed measurements, and a highly organised workforce. Today, the Ellora Kailasa remains one of the most extraordinary monuments of the ancient world. Its massive scale, unique rock-cut construction, and remarkable artistic decoration continue to amaze visitors and scholars alike. Despite many archaeological studies, key questions remain unanswered. How did the builders carve such a complex structure from solid rock with such precision? How was the enormous workforce organised? And what techniques allowed artists to create such delicate carvings in extremely hard stone? These mysteries continue to deepen the fascination surrounding the monument. The Ellora Kailasa stands not only as a temple, but as a powerful symbol of the ingenuity and ambition of an ancient civilization that transformed an entire mountainside into a masterpiece of sacred architecture. How do you think ancient craftsmen were able to carve the entire Ellora Kailasa from a single massive rock with such incredible precision and detail? Share your thoughts or theories in the comments below.